Afternoon live stream in the combo classroom. This one's a little earlier than some of my other recent live streams, so maybe we'll catch some other time zones of people live. But whether you're watching this in the present or future, I wanted to talk about some puzzles I've been designing and attempt to create some new sorts of puzzles. You see, I've been really. Ooh, I'm slid over. I've been really into recently certain sorts of grid puzzles and the mathematics behind their not only playing them but potentially designing them. And the most common grid puzzle known is Sudoku, where you put the numbers 1 through 9 in each. You have a 9 by 9 grid typically, which has 9 subsquares of 3 by 3 inside it. And that 9 by 9 needs to have the numbers 1 through 9 appear once in each row, column, and box, and you are given some numbers to start, already filled in. And so many of the puzzles I've been designing are filling in different sorts of numbers on a grid. Often I only use the numbers once, like making you use distinct numbers on a grid. And let me pull open some examples of grids. I tried looking at some online grid making things, like websites that had graph paper tools or whatever, and I didn't find any that were working right, so I used text edit here, which is like the super basic version of a Microsoft Word like text thing. And I found a way to create a table and smush the table so it looked grid like. And it took a while to do, so I copied it a few times for backup. So let's get that open, and I'll have some grids to illustrate my points. Here we got a grid, and this one doesn't have any numbers yet. It just has arrows, and I don't know if this is a valid puzzle. This was just an image that I wanted to, for one, save at least one arrow of each direction, because they'll come in handy, and I had to find them in a little tool menu thing. And also, so we can see the idea I have for a certain grid puzzle. Now, the first one that I'm going to show will be a puzzle I already designed that we're going to sort of double check together by seeing if it works the way it should. Meaning, how can I get this? I'll go on this side, where we're going to see if it only has one solution exactly. I was also going to note that although Sudoku is the most common grid puzzle, my favorite is this one called Star Battle. And there are many different ways you could have a rule for a grid puzzle and then some numbers or shapes already filled in that would make it a unique, different puzzle under that main rule set. And I've been trying to design those, but some of the puzzles I've been making to start just rely on a set of unique rules that are your list of information bits about where numbers may lie. And on each of these grids for the starting puzzles will be ranging from 1 to n, where n is the amount of cells. And we know some traits from that already, like if we're asking about square numbers, well, there will be n square numbers for an n by n grid, or the square root of the amount of cells for that type of grid. And we could have grids that are not equal dimensions. Some of my puzzles were like that, but here we'll be mostly doing 3 by 3s, 4 by 4s, or 5 by 5s today. And my starting puzzles rely on just a list of rules of where they may lie, not these arrows that will come a little later in the stream. Now, Wade Eberly said, do the numbers have to ascend according to the direction of the arrows? And you are actually correct for what I'm going to use the arrows for when we get to that in certain puzzles. And this is one type of puzzle that I was thinking would be a fun way to give some information, are that an arrow on each column or row, and perhaps we could put one for the diagonal too if we wanted, or the diagonals, but here just rows and columns, signifies that the numbers must strictly ascend if there is a single arrow going there, or strictly descend. They must go up or down depending on the direction you look at them, Meaning, for example, in this column, each number has to be larger than the one beneath it, and thus larger than all the ones beneath it. So it must strictly ascend. Here in this puzzle format, this would mean strictly descend, and I was using both arrows, which you could leave blank, but I think this is clearer to show it's known information that they are mixed. Because perhaps you would leave some blank in a puzzle that the viewer doesn't know which of these states it is, but here the double arrow implies it neither strictly ascends nor strictly descends. There's some moment of ascension and some moment of descension either way. Now, the first puzzle that we'll look at, that we're double checking one I already designed, just has a set of a few rules that go with it. It doesn't use the arrows, although one of the rules is similar to the arrows. I do want to get to the arrow type things because I think it would be fun to design whole puzzle structures that then people could play around with different ways of putting together. But here the puzzle structure is a little vaguer. It is essentially, for our grid, we have distinct numbers between 1 and that size. It doesn't have to be up here. I was just sort of gesturing up there, but it doesn't have to be there. And that we have a list of rules about it. Now, at some point, I will also attempt to mix these with my other favorite puzzle genre of sorts, which are knight and knave logic puzzles. We'll discuss those more another day. Here, we're going to assume all of our rules hold, that they are all definitely true. Now, let's shrink these a little so we can fit all of it on the screen. And here, we have our rules. Each cell contains one number, with each whole number from 1 through 25 appearing in exactly one cell. And if any of you want a challenge, you can see if you solve this before I finish my double check. Each even number that appears is directly above, and that means exactly one cell over, the number half its size, and each threeven number that appears, meaning multiples of 3, is directly above the number 1/3 its size. There are at least 3 columns that would have an upward arrow, is what this rule is saying. There are at least 3 columns where the numbers strictly ascend in size, from bottom being smallest to top being largest. And the final info that we have is that the top row, meaning these, contains at least 4 even numbers and at least 1 square number. Which number is in each cell? Now, how would we start here? Well, to begin, we might start with the number 1 and note, and the way I crafted this puzzle was sort of making up one rule at a time, seeing what we knew, what we could deduce from there, and then adding more rules until we were at the point where there was exactly one solution. There are many different paths you could use to solve these puzzles because numbers are interesting like that. But we'll go one way that I sort of was looking at the puzzle, was that when we have this first rule about even and threeven numbers, we know that the number 1 is going to have this whole clump of things near it that are within the size range where the double or triple of 1 also has a double or triple that will appear in here. For example, we know that wherever 1 is, and it could be, you know, somewhere down here for all we know now, but let's say it's here. We need, oh no, wait, sorry, this obviously is missing a bit. This is directly above, this is an important bit, or directly to the right of. Sorry for leaving that out. If anyone started the puzzle, you were probably thinking, well, that's impossible for them both to be directly above, because how are 2 and 3 both directly above 1? So, and directly above does mean one cell above that appears is directly above or directly to the right of. So let's say we imagine 1 in this corner, although we for now have some wiggle room of things sliding over, because above and to the right are where a lot of stuff's going to happen. And we know that we either have 2 there and 3 there, or the opposite. And we're actually going to, if I can do this without messing everything up, yep. We're actually going to have another one here where we show the other possibility. I'm going to move the rules out of the way now that I added the important detail. The rules go down there. And let's shrink this a little so we can see our two possibilities, because this is going to be kind of important to visualize. You could, if you wanted, for now at least, note that this is it, or that the reflection of this across the line y equals x is it. These are going to be sort of a flipped version of each other over this diagonal that would be like y equals x on a graph. So if this was the origin. And although you could do that in your head, the visual flipping, and make a little note here for yourself, let's draw them both because it'll make some bits clearer. So we know 6 is going to be there in either case because 6 has to be touching 2 and 3. And they both had to be touching 1. And it does work. It is either above or to the right of both 1/2 and 1/3 of it because it's even and threeven. Now, we can similarly deduce that we need the 9 there in this case, and we need the 9 there in that case because there's no other place if it has to be above or to the right, the triple of it. And we can also view this as numbers having to connect with their triple and their double if it exists. Now, in the range 1 to 25. Now, here we can deduce has to be 18, touches 6 and 9. And we can deduce that has to be 4, only room for that, 12, 24, and 8. This is the only way you can sort of lay them out because the only room for 8 is there, and then 24 would have to be there, and the only room for 16 is there. So now we can note that, good thing I put 1 in a corner for that test because the flipped version of that also touches the end at one point. They span either the height or width of it, depending which one it turns out to be. And so let's fill in this flipped version. That would have to be 18. So now what else do we know? Just from that rule, we do know that somewhere hanging out, we're going to make some notes of some things hanging out. 5 has to be sort of clustered with 10 and 15, because if a number has a double and a triple in this range, it needs one of them above and one to the right. And 10 is going to be touching 20, because that's twice that. So that's a whole cluster. 7, 14, and 21 are a little cluster. And these clusters could have a few shapes, but not too many different shapes. And then another little one is 11 to 22. And this actually accounts for all the even numbers and all of the threeven numbers that haven't appeared yet. So since it accounts for all the even numbers, our rule here where we note that the top row contains at least 4 even numbers can sort of come into play. Where we note, okay, here that would mean at least 3 of these have to be even numbers, and here it would mean at least 4 of all these have to be even numbers. Now let's look up here and imagine this can't be even here, because if it's even, it has to live above or directly to the left of, or above or directly to the right of the number that is half of it. And so that can't be even because neither of these would be half of it. So it would have to be all 3 of these in this case would have to be even. And here we need to use most of our evens. 10, 14, 20, and 22 are unaccounted for. And so to look at that, we would note that we need to use the 10-20 cluster in some way. And that takes up some space. So if we had it here, for example, 5, 10, 15, 20, that's a way of getting 2 evens up here, because we need all 3 of these to be even, since that can't. Then here, we're like, what do we have room for left? I could try and put my 11, 22 right here, because the 7 cluster wouldn't fit. But then once I look at putting the 7 cluster in somewhere, the 7 cluster would either be this or these flipped. Do I have room to do that? We'll say that right here. And then it could either be this or this slid up one. Those are the only places it would fit. And then if we look at our rule that there are at least 3 columns where the numbers strictly ascend in size. There's at least 3 up here that go bigger as you go up. We're like, okay, that one fulfills one of them. That ascends. This one could ascend. But then that one doesn't strictly ascend. That one doesn't strictly ascend because the only other option is this slid up, which doesn't change the columns really. And here, this one doesn't strictly ascend because even in the case where it was 14, we don't have enough numbers between that and 15 to not have something that dips higher or lower and messes it up. Or the 21 dips down and back at some point. So this whole thing doesn't work for fitting all the stuff in there. The other way would be to have this and this swapped. And if we did swap these, just to double check, 15, 10, 20, and here we had the 11, 22, we doesn't strictly ascend. This one has the problem that that one had before, so that one can't, and that one can't. So we can't fill the rule here where at least 3 columns strictly ascend from bottom to top. So it is not that one. So now that we know it's this case, we can zoom in on that and see what else we know. So we have to fit this stuff in right here. We need to fit in a few clusters. And we need to make sure that the top row has 4 even numbers. That means this has to be part of it because that has most of the even numbers. There's not enough others apart from that. So we have somewhere up here a cluster of different stuff, but we also have another clue. The top row contains at least 4 even numbers and at least 1 square number. And so which square number is unaccounted for? Only 25. So 25 is somewhere up here on the top row, and the other 4 are even. So now let's think of some ways we could place this. If we want to have room for all this and the whole 7 thing, and we need enough of them to touch the top with their evens, we need this whole thing, and at this point we need all of them to touch because we don't have the 16 up there in this configuration. And so all of these need to have their even parts touch the top. So we could have 5, 10, 15, 20, and 7, 14, 21, and 11, 22, or some way in which this part, this trio, or these 4 are swapped with each other in some way. So now we'll look at our rule, and the other one's going to be a 25. Now let's look at our rule where we need at least 3 columns that strictly ascend. That one doesn't. That one doesn't. That one doesn't. So, this configuration doesn't work. We got to juggle it around a bit more. So, looking at another configuration, this could have been slid over here. And we had 11, 22. And here we had our 7, 14, and 21. And this would be a 25 in that case. And in fact, we can note that 25 has to be tucked in the nook of the 7 thing. So we basically have that square, these 2, and that square could sort of shift around. Now here, could we have this strictly ascend? Possibly. Here, this one doesn't. This one doesn't. And this one doesn't. So it doesn't quite work because at least 3 of them don't strictly ascend. So now let's imagine another configuration. We've noted now that the 5 cluster cannot be there. That doesn't work. So there's the 5 cluster must be there or there somewhere. And if we test a few more possibilities, we can find one that works. this made this strictly ascend, which helps with that a lot, because we want, we need at least 3 of them too. This one, if we want it to strictly ascend, could go over here somewhere. It wouldn't be able to in here anyway. So if we move it all the way over here, then we're like, okay, we're getting close. We could have enough of them strictly ascend, because that one does, that one does. That one doesn't even have room to, because of the 24. And this one could. So, we have now, that would be, well, let's see. This is with the 5 square there. Wait, in this formation, this one can't. So, let's see. What formation does make this work? Let me think in my head. I feel like there was some configuration that made this work. I'm going to check another document of mine to check the notes, just to make sure this one works, because this was just a starter trial puzzle that I already hopefully invented. I think it works correctly. Let me double check something. Okay. Yeah, so what we end up wanting is, we could fiddle around the possibilities. Since I already invented this puzzle and I'm sort of double checking it and showing you the strategies of how you would double check something like this and what sorts of strategies may show up in our puzzles. Well, I'll speed through that and note that the formation we end up wanting is to have this cluster over there, and the 5 cluster right there. That's the way of fiddling around those moving pieces, such that we get enough evens on top, but we have a chance at our thing where we have at least 3 that strictly ascend. So how are we going to make at least 3 strictly ascend now? That one doesn't work and that one doesn't work, so it's got to be these other ones. And that middle one can't have a 14. We already used that, so it needs to have a 13 to strictly ascend. So what about this one? The ones that are remaining in this range are only 17 and 19, so we do know that it has to be those to strictly ascend, and the only remaining one now is 23. And that solves our puzzle with these clues. So that is an example of one of my puzzles that doesn't rely on a bigger original puzzle structure, apart from here's a grid, you have distinct different numbers, which even is one of the rules. It's sort of just a list of rules that give you your data. You could even not even start with the grid and just have this written out and say each cell in a 5x5 grid. But this is the rules of that sort of puzzle. Now, what I wanted to test out today is to what degree we can design puzzles that don't need a bunch of different sentences, that are sort of a couple simpler rules than this, that given certain symbol arrangements or different arrangements of shapes or number ranges or things like that, would be able to generate multiple puzzles in a category, sort of like how Sudoku or Star Battle have a simple set of rules that you can design many puzzles within. So to check our comments, let's see. And there are some interesting ones here. Thank you. These were the rules to someone who asked. Now we're going to go to another idea I had, which is, why don't we try having grids that we are going to have symbols, sometimes maybe in the shapes. We could shade them in a certain color if we need to, and say what the shading means for a type of puzzle. Or we could try to put symbols just for rows or columns that tell you something about them. Examples I was brainstorming of things they could tell you about them, given that we're using distinct numbers, could be the amount of even versus odd numbers in them, or a puzzle could involve the amount of square numbers or the amount of prime numbers or something else like that that are in a given line. And you could have maybe cells shaded as well if you wanted, like the shaded cells are where the primes go or where the squares go. Or my idea with the arrows, which I don't know if this puzzle even works with the set of numbers, even without other constrictions. We're going to remove a bunch of the arrows, but what it means is that this number must be smaller than that, which is smaller than that, and etc. If the arrow is going that way, it strictly ascends. This one would mean this ascends looking that way or descends looking that way, the numbers. And having two of them, I'm using to mean it doesn't strictly do either. There is a point of fluctuation where it goes from ascending to descending or vice versa or both. And theoretically, you could even make a version where it shows how many times it changed directions with sets of arrows, like it started ascending and then it descended. But here we're just using it to mean some mix. And if we left one blank, we're going to assume that means don't know which category. And theoretically, one way you could design a puzzle, which I'll come up with some nickname for this later, but one puzzle on its own that I think would be fun for people to design would simply be you have those rules and you design a puzzle with certain sets of arrows given and a few numbers already filled in. And some that I was experimenting with were like, what are some of the extreme cases? Does it work even when, does it work even when we have all of them ascend or descend in a certain direction? Uh-oh, I lost my arrows. Okay, I'm going to Command Z all that because I don't want to have to re-find all the arrows. We're going to make a little arrow collection over here. This will store one of each arrow. Or will it? Okay, I got to get one more. I have to go back to that emoji menu or whatever. Emoji and symbols. This is where I was. Yeah. I need down. Okay. All right. They had dotted versions of them too if we ever need two types of arrow. Okay. For now, that's our little arrow collection. And I was wondering what happens in some extreme examples, like when all of them are ascending or descending in the same direction. And even in cases like this, where you might expect it to like only have one set of numbers that were really obvious, there are multiple ways we could end up doing this. I could 1, 2, 3, 4, 5, 6. I sort of just have to fill in the gaps in a certain way, and there's tons of ways I could be doing this that is making it follow these rules. So, sets of arrows, unless they are really specific sets of arrows, which maybe don't even allow any solutions, those are sort of the most interesting mathematically, or I guess it's equally interesting maybe, the times where you start designing a puzzle and you realize a certain clue can't be added because it would make it impossible. And that shows some little impossibility in math. Like, you cannot have a grid with this happening and this happening. As a really simple example, we can't have at the same time a row that is purely odd and a column that is purely even. Because what about the number they cross on? Any number in any column touch here. So what about that spot? So there are certain things you can't have as clues at the same time. And those will come into play when we mix this with the logic puzzle form someday of knights and knaves. Wade was thinking, what if we have a puzzle where the prime factors of a number must go in the squares orthogonal to that number? Certain squares can be blacked out like a crossword. That's also another thing to note. If you had blacked out squares in a smaller range of numbers, that could work. And the prime factors actually is pretty similar to a thought I had. It actually works on grid sizes of certain sorts to have numbers have to touch all their factors. but you need the right number range that sometimes starts higher than 1. You already need to exclude 1 from being included in all of them. But for example, I was testing one version where, ignore the arrows for now. If we started from 3 and went to 27 would be all of the whole numbers in this range. And if we had them have to touch all of their factors, meaning 3 would have to be touching a bunch of stuff, and we'd have to figure out, I didn't double check if this is even possible for all of them to work, because like 9 has to touch 18 and so does 3, but 6 should be touching that too, and 6 needs to touch 12, but that needs to touch 4 somewhere. 4 might not even have room to be close to 3 with all the multiples 3 has to touch. And so prime factors, that is another one maybe I will try in a bit, Wade, and maybe if I take a break at some point, I will show you folks one of the puzzles I've already designed that relates to factors in a way like that. Another rule that I figured would work on larger sizes of puzzle, because otherwise the larger the grid, the larger the starting number of the range that you're doing is if you include all factors, or even eventually prime factors, because if you had a big enough grid, because numbers can only have 8 neighbors. You could also say only 4 neighbors if you're not counting diagonals. So these ones we're calling the orthogonal neighbors, and we're calling these neighbors in general. If we don't specify, we'll assume we mean diagonals are in there. And another similar twist on that I thought would work for larger grids, even starting from the number 1, not including the number 1 in this, but any number larger than 1 would follow the rule where they can't be neighbors with any of their factors. So 2 would have to be surrounded by odds, for example. So 2, you'd probably want to put in a corner to not use up all your odds or something. If you were solving it, maybe there'd be a point where you wouldn't have enough odds to go around. Some puzzles you can even prove things about just using parity, using traits of even plus even is even plus odd is odd, and stuff like that. And we also got a recommendation from someone named Phi, or Phi, depending how you pronounce it. I mean, like, I know it's the mathematical symbol in Greek letter, but it is pronounced multiple ways. The modern way is more like Phi, but it's originally it was pronounced more like Phi. But here's the thing. A lot of people talk about that. Not a lot of people mention that if we're going with the original pronunciations, pi becomes p as well. So unless you're going to start calling pi p, maybe we should allow either pronunciation of phi/phi. Now, they recommend totals of column row to eliminate many other possible solutions to a smaller set. And that is another one that I was sort of dodging that because I've seen some puzzles do things like that already. But with the right combination of little rules, we can make a unique puzzle. And that is a possibility that a number would signify the sum of the numbers in that row or column. Several of the puzzles I've designed so far give you some clue along the lines of, like, there's at least one row where the sum equals one of the columns. I didn't do that as much on the 5x5s as the 3x3s, because it got kind of annoying to have to do all the addition in your head, testing multiple possibilities. Just felt more trivial when you had to add 5 things each time and think through each one more. So here, why don't we see what possibilities would we have if we were given a certain set of arrows to design a puzzle? Because when we take little breaks or I'm chatting or something, I'll show you some I've already designed, but now we're starting from scratch with all we know so far is we are using at least one rule, which is that these arrows, if placed there, signify whether something is ascending or descending, if that is known knowledge. Now, let's say we had certain numbers in here and we had the ascending and descending thing. Some combinations turn out to be impossible. Because if I had, for example, let's say they were all going this way. I mean, obviously some are impossible if I fill in enough numbers. But some with even just a few numbers, are impossible. And an example of that is, okay, who cares if they're even, is I can't even have 1 down there and 6 up there, because there's no way to get up to the 6 from there with that one having to be upward from there. And we got up to the 6 from there, which was also from there. And we have to get these. So it's like if I was like 2, 3, 4, okay, I guess 5, 6, but then what goes there? Or if the 5's there, what goes there? So with a lot of arrows at play, even though I noted that things like this, which are, well, let's flip these. I think I meant this more than I meant the other one. That's actually what I meant. The other would be impossible, because that would mean one got bigger than something. So here we note that if I have that cell, if I have a 1 down there in this arrangement, no matter what, that's bigger than 6. Maybe it would help to use bigger thans, like inequalities, if you were trying to solve one of these. So to design one, let's say we were given that that's 7. We would need to maybe be given one more to, wait, let's see. This, yeah, this way would be a slightly different problem that I mentioned of coming from up there. It would be a problem that we have to get up there, and we have to get up from there. So how large would this actually have to be with this arrangement? We could have 1, 2, 3, 4, but we also need to have 5, 6, 7. This actually has to be at least 8. So we can say bigger than 7. So let's say we knew it was 8. What that would tell us is that all of the low numbers are clumped around here. But what if we knew something more extreme further out? For example, what about this right here? Oh, squirrel alert. Oh, it just jumped over the fence. Never mind. So here, if we have a 1, then, well, even if we don't, we would know the 1's somewhere on the bottom. Let's say we don't know where the 1 is, but we know that here we have some number. Now, some of these are impossible. So the lowest that this number could be would be 1, 2, 3, 4, 5, 6. We have to sort of build upward to get there with this type of arrangement. And that would imply, would that imply the 1 is in one of these spots? If the 1 can't be there. The 1 definitely has to be in the corner in this arrangement. With these arrows, you automatically would have to know the 1 would be here. Any other spot is bigger than something on one of these arrows. And the largest number would have to be there. So we definitely know those just from the arrows. Now, with that said, there's many ways to lay it out so it would work if we didn't have other clues. But if we knew this was 6, for example, that would concentrate all the low numbers around here. But let's try something a little trickier. What if we knew this was, say, 11? What would we be able to deduce from that? We would know, well, we need to get there using 1, 2, 3, 4, 5, 6, 7 cells. So a lot of low numbers are here, and all of these ones would have to be smaller than 11. However, we don't know enough to eliminate the small numbers from being elsewhere, because we don't have to use all of them to get there, essentially. So what if we knew a few details? What if we knew an 11? What if we knew something weird? What if we knew that an 11 was there, but that something smaller was there, but a 10 was there? So how can we go about this? We're going to need to probably have a different fork that goes to the 11 and goes to the 10. So we would need something between 1 and 11 there. And then we got to sort of snake up to the 10 there. But we also need to get to the 10 from there. So let's see. This actually has to be pretty low, because we need to be able to get to the 10 from there. And we need to be able to get there. So that requires 6. Let's say, for example, and that's not going to work. That's impossible in this arrangement. So I think in this arrangement, the diagonals might have to ascend. Now, other things, if you compare, like, what about that versus that? There are different ways to get to, and don't necessarily have to strictly ascend or descend, because some have more of one direction or more of the other direction. But I think the diagonals have to strictly ascend. So let's say we didn't know all this, and we only knew stuff about the first 2 columns. What would we know from this? If these, let's say all these had to go that way. Or actually, maybe it'll be a little easier to visualize if we imagine all columns have to go up, but we only know so far the bottom 2 rows must ascend. Well, let's see. We know the 1 has to be in the bottom row somewhere, so we can put a little note about that. And then we know from there, to strictly ascend, the 25 has to be somewhere on that top row. Now, what do we know about these cells? Well, these cells need to be at least 3 smaller than 25, but they also have to be a bit bigger than something, because this one, for example, had to ascend all the way from there. Now, here in each case, this has to be a bit bigger than down here. So what does that tell us? Let's say we know the 1 is there, so that we can, well, actually, yeah, the 1, is that the only spot it could be? Yeah, in this arrangement, the 1 can only be there, because it has to be on the bottom row for this rule, so it has to be left for that rule. So, and a note for anyone coming in new, all right, these show which direction a row, column, these show if we are given a direction, a row or column shrink. A row or column strictly ascends. And we can think of ascension as reverse descension, so we'll think of all of it as strictly ascending if they do this, and just that some ascend that direction or that direction or that direction or that direction. Even though the up-down ones, you kind of think, well, ascend means going up, but let's just assume it means that the numbers follow a progression in one of the directions where they're each larger than the last. So the 1 would have to be here in this arrangement. And now, where could our 2 be? Our 2, could it be either of these spots, maybe? Because if we had the 2 there, that could theoretically work. And if we had the 2 there, that could theoretically work. So the 2, we don't quite know exactly which of these it's in. It has to be in one of these. So if you were doing the puzzle, you could have some way of taking that note to yourself. And then we can try and think about where other stuff goes. Now, to make this puzzle work more interestingly, what we're going to do is give ourselves one extra rule we're going to try. And what we're going to try is the one where, let's see, do we have enough room for our factor rules? If we look at all factors of a number having to touch the number in some way, that won't quite work because of all the evens and stuff. What if it had to be either neighbors or in a row or column with it if it was a numbers factor? Then 2 might have enough room to fit all the evens. Apart from 2 in this range, there's 11 other evens, and there would be 12 spots it can reach. So that does work. I think, so this is going to be our rule for now. We're going to make a rule for this puzzle that, and this can't be directly expanded to larger puzzles. If you had a larger grid, you'd need to make an exception probably. No, if you had a larger grid, would it work? Yeah, with a large enough grid, you'd need to make an exception where 2 doesn't count. All factors larger than 2. Instead of we already need to make an exception of all factors larger than 1, if we're including that. 1 sort of gets a freebie where it can go anywhere under that rule, but it's much more restricted by any arrow-related rules. So what we're going to say here is one of the rules we're going to add to this puzzle, apart from that we're given arrows, is that each number... Wait, will this work? It won't work if all of these have to ascend. That one we're going to leave blank. Each number is either neighbors with, including diagonally, and let's shrink this a bit, or in the same row or column with each of its factors larger than 1. So here we can note that 2, even just given this arrangement, doesn't fit that many places. It has to be close to the center. If 2 was on an edge, the amount of things that affects is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's not enough because there's 11 other even numbers that 2 has to be neighbors or in a row or column with. So 2 has to be in one of these more inner squares. Now, actually, it would, I think, work with this arrow here. Does 2 have enough room here? 1, 2, 3, 4, 1, 2, 3, 4. Yeah, 2 can go there. So this is, if we have these arrows and this rule, in fact, with these arrows, 2 must go there because the other places it doesn't have room. And in fact, even just with these arrows, we would be guaranteed that the 2 had to go here. Because in any of the other center-like spots, where it could theoretically have also been in one of these, are too high up for the arrow to work. We would also know the 1's right there. So, but that used up one of 2's neighbors. How many neighbors now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That means all of these squares, we're going to highlight a color because we know that they're even. And all we've been given so far was the arrows and this rule. So all the numbers we're filling in and stuff is stuff we're deducing about it. So here, to choose a background color, we're going to make these yellow. Did that work? Okay, it kind of worked. It highlighted the text zone. And wait, that one was bigger for some reason. All of these must be even, the ones that we're coloring yellow. All right, and the others must be odd because that used up all of the evens. So, what does this tell us? Well, the evens that we have, and let's just take some notes somewhere around here. We'll just make a little more room down here. And we'll take some notes saying, let's see, I want to make sure we can see that fully. Yeah. That the ones remaining, these even numbers, include this list that we're going to try and trim numbers off as we know more details. So, some of these need to touch others of these as well. For example, 4 and 6 are going to touch a bunch of them. Even ones like 12 are going to touch a bunch because it has one multiple that it's a factor of, and it has a bunch of stuff that are factors of it. So small things or highly divisible things are going to have a bunch they need to touch here. We can note 4 touches 8, 12, 16, 20, 24. And so that's 5 numbers 4 has to touch. They all have to be even. That doesn't even work. So this arrangement doesn't even work. Those are impossible. The 3 arrows being there with that rule. So That's sort of interesting. It seems like a failure at first. However, let's remember that that gives us some cool info. If this is our rule, we can't even have just those 3 arrows. A small amount of arrows might give us a lot of info if we hit the sweet spot where instead of 0 solutions right there, or many solutions if we don't give enough info, we have 1 solution. So let's, and who knows to what degree we'll invent successful puzzles today, but I believe we'll learn a lot of interesting techniques and variations that I will surely, and hopefully some of you will also, explore. And maybe some of you will invent your own variations of the combo grid puzzle. Now, here, let's see what happens if we have a little less restriction. The problem with that is that I don't even know if this works, this rule. Because even without the arrows, if the 2 was there, these have to be even. But the 4 needs to, like, be touching a ton. Oh, no, it needs to touch 5. So it could work if it was here. It didn't work down there because 1 was in the way. If we have this whole grid, we wouldn't actually need all of these to be even, because that's 12, and we need 11 other evens. We had the number 1 taking up one of those spots when we knew the arrow did that. So let's say we don't know that arrow does that. And maybe that'll give us enough info. The thing is, now 2 has a few different places it could live. We wouldn't know directly that. So let's just see what we can demonstrate about these numbers. What could the 2 and 4 cluster look like? Well, we're starting from scratch here with these rules. So the 2 can't be on an edge because an edge, or including corners, don't have enough neighbors to have this factor rule work. The 2 has to be in one of these more inner squares, but it has to specifically be touching some of its neighbors in a special way. Like 4, for example, would have to, this is just one possible arrangement, would have to touch 8, which also has to touch, or be in the same row and column with, 16, and 4 also has to touch, wait, no, but 16, yeah, it's in a row with 2. Has to touch 12, which has to touch the 3 related stuff somehow, because 12 has to touch 3. Now, here, the 3 cluster is going to be interesting, because it has to, somehow 3 has to be touching or in the same row with 12, 15, 18, wait, no, 15 isn't one of the evens we're looking at, 12, 18, and 24. So we could have 3 hanging out like there or something, but then 6 also touches all 3 of these. So that 6 would have to be like in the line with them or something like that. So let's say we have a small amount of info, and our small amount of info will be 1 specific arrow. The problem is that I don't even know if that arrow works with the rule. If we have it there, I guess the 2 maybe could be in one of these spots. So otherwise, the 2, or it could be here, I guess. It needs to dodge the arrow in a way, but we have to make the rest of the numbers work as well. So let's say, to test a more extreme case where 2 is pushed over, it's there. And we're going to see if that works if we have some rule like this. This one has to go upward. And I guess the other possibility, we'll remember, would be this flipped, which for now is symmetrical because we don't have any other arrows. So we need 1 arrow going this way too, so we know sort of the orientation, I guess. So let's say we know this and this. Well, where could our 2 possibly be? Let's test if it works to have a 2 there. If a 2 existed there, it's going to need to touch a bunch of stuff, and this row needs to be increasing. So this we could try. Well, 4 can't be there, though, is the problem, because 4 needs to touch a lot of stuff. 4 needs to touch 5 neighbors, we noted. And the only way to do that here would be at one of these cells. So one of these cells could be 4. And the problem is that doesn't work here because it can't be there. We would have to build up to it with smaller numbers that don't fit. So we would have to say maybe the 4's there. Now, the 4 needed to be touching or in the same row with a bunch of stuff. And actually, I guess the 4... No, it can't be there because of these arrows. Another possibility we could note would be the 2 being there or there. So I'm kind of marking these to note that we were sort of testing one of these possibilities of where the 2 could be, because any of those so far could theoretically work, even though I doubt the higher ones are going to work, because stuff over here would get weird, but maybe. So here, if we have our 4, it would have to be there if the 2's there. And is that true? Would this have enough? 1, 2, 3, 4, 5. Oh, no, I guess the 4 could be here. The 4 could be one of these. But the 4 needs to be in a row or column with a bunch of evens. And we have 12 cells here that are touching the 2 or in a line with it. And of those 12 cells, 11... not counting the 2 itself, because I didn't count that as a cell, are even. So we can't have many odds. However, some of this stuff needs to be touching the mess with 3. 3 needs to be connected to 9 somehow, but it also needs, and to 21 and 15, which has to touch 5. This is a tricky bit we could look at. 15 needs to touch 5, but this is just a random orientation for now. 5, well, that wouldn't work there because of this line anyway. So 3 and 5 have to touch 15. But 5 needs to touch 10, which is even. So 10 has to be in some cluster near there. This works because they're in a row. And then 5 and 10 need to touch 20. Or be in the same row, I guess, can work. Because these are still close enough to the 2. So this is one orientation it could maybe work. Let's give ourselves another clue so we get enough knowledge. Now, if we only have that one arrow, which told us the 2 must be in one of these or a flipped version of that, let's say that we are given a few arrows that are going to be, well, if we had that up there, these sort of cause some of 2's neighbors to do a particular thing, where those have to rise to that and these have to rise to that. And what if we were given a single number here? If we were given, let's say, an 8 in the middle. And we're going to put that one in bold because that's the one we were given before. If we find a good puzzle here, we'll remember that was pre-knowledge that we already had. And now where could the 2 live in this thing? Well, the 2 has a bunch of neighbors, And 8 needs to be one of them. So you would think at first, maybe the 2 could be in any of these. The thing is, to get to this 8, there we would need to have a 1. That swallows up, if the 2 was there, that swallows up one of the 2's neighbors. All of these would have to be evens. And this has to be an even smaller than 8 in that case. So that would have to be 4. I'm testing if the 2 could be right there, essentially. So that would have to be 4. And 4, 8, and 2 have to be lined up with 16 somehow. So 16 would have to be either there. Either there or there. And no, is that right? That doesn't touch all of them. Oh yes, it does, because in a column will count. So if we're there, that could theoretically work. And then things could keep going. But one issue we're going to hit soon might be that 6 needs to be one of these, and 12, and 18. And those all have to be ready to touch 3. So these ones would have to include 6, 12, and 18 sort of near each other in some way. In fact, 12 and 6 need to be lined up in some way. Now, there's a lot of ways in which that sort of thing can work, but this is a pretty complicated clue. And I think there's a chance I might move on to another sort of clue soon. It's been an hour total so far. And I do need to take a real quick break and refill some coffee and run to the bathroom. But while I do that, I will give one more of the puzzles I have already invented. Now, these have not been double checked, so I'm pretty sure the puzzles that I'll show that I invented before this, the ones I show, I'm pretty sure that they work, but there's a chance that there's multiple solutions, or some chance there's 0 solution. And so you can double check it if you want, but I'm pretty sure that these ones I'll share will be full puzzles. And here we have one more puzzle that is sort of like the these I'm just going to X out because they don't exist. We're using a 4x4 grid. Oh no, wait, not on this one, down here. So we're just going to do a 4x4 grid for a moment for this puzzle that I'll share. And to do that in a really casual way, we're going to X out this part of it. Now, fun fact, remember... Oh, I'm not even showing it. Fun fact, remember that when we do what I just did, we cut a square into a smaller square by subtracting an odd number, because square numbers are the sum of all the odd numbers up to some point. I was even thinking some puzzles could be cool if there's like stripes that are drawn in where you have here, you have this band, you have this band, and etc. Now, for this one, the way this puzzle I previously made that I hope works is we have a 4x4 grid with kind of similar rules to the previous one that I showed at the beginning of this. We know that even numbers, so here I'll note numbers 1 through 16 in distinct cells. Even numbers are either directly on top of or directly to the right of the number half their size. And then we know that 3 even numbers are directly on top of the number 1/3 of their size. Which, before we had, it could be to the top or right for both. In this one, 3 even numbers we know are on top of. And then We know also that multiples of 5 are neighbors in some way, including diagonally as a possibility, are neighbors in some way. So that's one cell apart, counting diagonally, we mean by that, with the number 1/5 their size. And the final other bit of knowledge we have here is that the sum of the top row is equal to the sum of the furthest right column. So if anyone wants to try to solve this one while I run inside for a couple minutes, I don't know if it's solvable in a couple minutes, but maybe. I'll be back in 2 or so minutes, and then we're going to jump into designing some more new ones. Although perhaps I will show an answer to this real quick. Maybe I'll leave this one as an open puzzle. So either comment it now or after the fact if you're watching this in the future. Also, feel free to leave a comment if you solve this one. Or please let me know if I made some mistake here somehow. Okay, I'll be back shortly. All right, folks, I am back, and hopefully one or two of you tried that, the beginning of that puzzle. Leave a comment if you solve that later, but feel free to wait till after the stream. It'll be posted as a video you could comment on. Now, we're going to go to inventing a new puzzle, and we are trying some things with arrows, but the arrows were very restrictive with, one sec. Let me readjust my documents of my notes real quick. So, we're going to try and use some arrows somehow. Maybe we will incorporate these arrows. But we're going to invent a new rule. Let's say that all we're going to know for this one, let's say that all the columns ascend. And we're going to make a not super restrictive rule. And let's say we know this, because this tells us 1 must be there and 25 must be there. Because the bottom of each of these must be the smallest of it, and then the smallest must be there. So 1 must be somewhere in the bottom, and this tells us it must be on that side of the bottom. Same with 25 in an opposite way. Let's say we know a particular mini rule. Let's say we know that square numbers larger than 1 are directly above their root. Well, is this even possible here? I think that rule might make an impossibility, because 5 being there would have to go like 4, 3, 2, and that doesn't have enough room to catch up. So that doesn't even work there. Let's see. And we can't have that with all the arrows. So let's make a different rule. What sorts of rules could work here? Let's say that we're going to try the opposite of what we tried before. Numbers cannot touch any of their factors larger than 1. And they cannot be neighbors, including diagonally. They can be in the same row or column. But let's say we know that for now. Well, 25 being there, which we know from these arrows, would tell us that all the multiples of 5 are spread out somewhere else that aren't in that range. And we don't know too much from that. So why don't we say that we knew one additional number? And this is actually the only number that we would be given so far in this puzzle, apart from that rule and the arrows. But because the 1 and the 25 we just deduced from the arrows, let's say we're given a specific number. Now, to figure out what number I might want to give in a puzzle, let's find one that would give us some starting knowledge of 1 or 2 trails of numbers that must lead to it. For example, if one of these numbers is a certain size, to get to them, we have to already have gotten there from 1. And this number couldn't be smaller than, say, 4, because we have to go 2, 3, 4, what? And so let's say we knew mostly where some stuff was. Let's say this was 5. No, that would be exactly where stuff are. Let's say we knew this was 6. This is towing the line between giving too much info, which is 5. You'd know it's exactly 2, 3, 4. And, well, let's actually try the extreme case with 5. We'll probably end up wanting to try 6 next, which is less restrictive. But let's say 5 was the only clue we were given at the start, apart from these arrows. Well, we said that numbers cannot touch any of their other factors. That works with 25 and 5, but now we know that a lot of these can't touch certain things. So this right here can't be a multiple of 2, 3, or 5. And if it's not a multiple of 2, 3, or 5 in this range, it has to be a prime. So that's some prime there, we would know. And what else could we deduce here? Well, 5 can't touch any multiples of 5. So those all have to be clustered somewhere else. And let's see, what could this cell be? It can't be a multiple of 4 or 5, but we could even have 6 there theoretically. This has to ascend from 5, and that has to go there. So we might need an extra piece of information. Let's give one more number. And we're going to see from each deduction how many numbers or arrows might be necessary. Let's try something a little different. Let's say we didn't know these, and we were given a larger number, but we had this arrow as well. Well, now we would have to cross 6 cells to get there, so 7 would be the minimum number that would tell us stuff, although we could have a few paths of getting there. And let's see if any of those paths are possible with our factor rule. So one path would be, here we have a 2, and we come up from here. That can't touch 3 or 4 there, so the 4 would have to be somewhere a little further. The 4 could be there or down there, maybe. And we could have the 3 going from there or the 3 going from there. So far, so good with our factor rule on either of these paths. Let's say that was our path, and we went 5, 6. Wait, that's not enough room. We need a little more. We need this to be an 8 at minimum. And so now we know that the 4 wouldn't be there. If we were given an 8 there, now I'm saying, because I realized 7 was too extreme and didn't work. So 8 couldn't touch the 4 there. 4 would have to be somewhere closer. And so the 4 can't be too close to the 1, because we have to go sort of in order to use them all. If the 4 was here, for example, then we would need to have 5, 6, and maybe that would work. So the 4 definitely has to be one of these. First, let's see if the 4 could be there. Well, no, because this would have to be 2. Uh-oh, we're going to have a problem with the 4 and the 2. I don't think this even works with the 8, because if I climb up with my 2 next in one of these directions, well, the 4 had to be one of these cells to not touch the 8. So that has to be at least a 9. So let's say we were given a 9. We're sort of crawling up the impossibilities until we get to the point where it's possible and see how much data we would get from that number. So given if that was a 9, and remember the 1 and 25 are just deducible by these arrows, then we would need to not have the 3 anywhere in there, but that's okay because we want the 3 closer anyway. Now, we actually, with a 9, don't need to use all of the numbers. 2, 3, 4, 5, 6, 7, 8 is 7 options for 6 slots. So we're going to be able to basically skip one of those. So this actually doesn't give us enough info quite to start going. Either of these could be the 2 could be in one of these, or a 3 could be in one of these. We do know these numbers can't be too big because these have to be smaller than 9. So let's just take notes that we know like that so far. That has to be smaller than 9, and that would have to be smaller than 8 for sure, and that would have to be smaller than 7 for sure. And we would know that same chain, oh no, separate, from here. Then we also know that this one can't be a 3 for certain ones of these, so we're starting to limit some possibilities. We would know that the 2 and the 4 can't be touching. And so unless we skip the 4, because we're allowed to skip one in this case. So we may need one more piece of knowledge here. Let's say that this number here was something that could give us a clue. Maybe even this number could be an 8. Well, if this number was an 8, then these shrink a little bit. we would need to distance the 4 if it's you. And now we would need to use all of them, all the numbers in this gap somewhere. All the numbers 2 through 7. So here, if we have this one, can't be a 4 because of the 8. And we need the 2 and the 4 somewhere. In this case, since we're crawling up both directions, we are going to need the 2 in one of these. And it can't touch the 4. And the 8 can't touch the 4. So the 4 would have to be here, and the 2 would have to be here if we were given that 8 and 9. Meaning 3 would have to go there. 5, 6, 7 would have to go there. So I'm pretty sure with that 9 and 8, if that was known, we would know this. Now, the factor rule isn't giving us too much trouble in this case, because we've sort of buried some of the numbers, like 5, that are going to show up as factors a lot. But right here in these cells, those are going to be more limited by what factors they can touch. This right here has to be a prime because it can't touch 2, 3, or 4. This right here can't touch 2 or 3, and, oh no, wait, it could be a prime or, wait, the only multiple of 5 that isn't a multiple of 2 or 3 here is 25, and that's all the way up there. So, this also would have to be a prime just by touching the 2 and 3, because it's not 25. So, those are both primes, and what else can we deduce from here? Well, this right here is not a multiple of 3 or 4. Does that have to be a prime? Let's see. Well, the other cases would have to be multiples of 3 and 2 that weren't multiples of 4, such as 6, which is already used, 18, which can't be here because of 9. 9 is a factor of 18. Or, that should be, wait, no, 18, yeah. Or, yeah, 30 would be the next one. That could be a problem. So this has to be a prime as well. There's no other numbers that aren't a multiple of 3 or 4. Oh, no, wait, it would have to be non-3 then. I was thinking about that wrong. Let me double check this in my head. It has to be... Well, let's just really quickly run through the composites in my head. It can't be 6, 8, 10 it could be. So it's not definitely a prime. It could be 10. So that might be about as far as you'd be able... Oh, no, wait, this doesn't work. These are bigger than these. Now, since that was demonstrated by the 9 and the 8, I think the 9 and the 8 together are impossible because these weren't bigger than these. I forgot that all the columns have to ascend. So this is another impossibility we've found. This sort of puzzle's sort of hard to design, but I imagine that if you did it right, we might be able to make it work with just a few numbers as givens, or even just a set of arrows. So let's say we didn't know that exact thing. If we just knew that was 9, well, let's say we knew this was 9. Then we would know we have to creep up there, and we know these have to be bigger than these. So, or these have to be bigger than these. So we'd know 2 has to be there. And we could have 3 there. And, well, they can't touch their factors, actually. So 2 couldn't touch 4. This actually won't work either, because we're not going to have enough room if I can't touch the 4 right there. So I'm pretty sure this would have to be a 10 maybe, or be closer in some way. This is a strange configuration. I think we're going to have to remove an arrow or two. So removing this arrow, we still know the 1 and the 25, but if we had a certain given right here, it wouldn't tell us quite as much unless it was on this line. If I put a 5 there, we would know exactly what it was. So we don't want something quite that simple. But let's say that we know some numbers around here. If this was given as something sort of large, or let's see, if this is given as something relatively small, this has to be relatively small as well. If this is given as a 3, we need our 2 there. Similarly, if this was given as a 5 without the 3, it would have to go like that to fit itself. And if that was given as a 7, it would be similar. Let's say we were given one of those. The 5 actually wouldn't work. That'd be impossible because the 2 and the 4 can't touch like that. Let's say we had the 7. Does the 7 work? If we knew this 7, it would imply that it goes 4, 5, 6, 7. And that does work with our factor rule so far. Now, this would have to be just something larger than 7, should work. That's not 8 in specific because of that 4. So I think that 7 would work as one piece of info you could put in an easier version of one of these puzzles. And why don't we try that and another number? Because if we can design an easy version of the puzzle, that'll at least show that the puzzle's possible. Now, well, and the puzzle is possible with some configuration of arrows, but if it's possible with these and with certain givens. So, what if we knew something here was something relatively small as well? Only one arrow is sort of talking about that. Let's actually, instead of adding a number yet, what if we add an arrow? Is that going to be possible? The arrow couldn't be on any of these because we wouldn't have enough numbers to get there and up. But maybe we could have an arrow on top, that this one goes strictly upward. That could be helpful because here, this has to be bigger than 7. But it couldn't just be 8 or something, because then we wouldn't have enough to go strictly upward from there. The range it could be is larger than 7, but it would have to have room to go 25, 24 at the minimum. Or wait, to have enough room for these, it would actually be 7, 8, 9, 10, 11. So it would actually have to be at least 11 to have room for this to even work. So, if we did know that was 11, that would give us a lot of info and maybe make the puzzle work, because we're going to kind of close in a little box of where other numbers can go. So, from 11 there, it would have to go 8, 9, 10. And this does work with our rule so far. Oh no, but we're not going to have enough numbers to get up to those. So 11 doesn't even work. We need enough numbers to get up to those. We would need a lot. We would need 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 9. Or no, wait, from 7. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, yeah. And 20. So even 20... there would tell us a lot. Having a 20 there, and this would be that our givens for the puzzle were a 7 and a 20, the others we could figure out, would tell us that all of the numbers from 8 to 19 have to be somewhere within these cells, and the numbers 21 through 24 have to be in these cells. But that wouldn't even work because 24 would be touching either the 4 or the 6. So, that wouldn't even work. If we had this be 21, how about? That wouldn't work because of the 7. What if this was 22? Would that give us any info? Or, let's say we knew, Yeah, if that was 22, would that give us any info? So here it's 12 after 7, so up through 19 would be the amount to fill there, and then there's 20 and 21, so that leaves 2 extras. The 24 can't be over here, so the 24 has to be within there, so that leaves 1 extra. And let's see, what about the 20 can't be down there, but the 20 could theoretically be there. So almost all the numbers in this case from 8 through 20 to 8 through 21 would be in here, but not quite all of them. So that's not quite enough to deduce that row. I want to find a way to give some clues that close this in a bit to some degree. So what we're going to try and do is well, we have that arrow already. We can't have an arrow going here. So what if we knew some number more around this corner? What if we knew, for example, that this number was something relatively small? What would that, or what about this number? We were trying from here, but let's see if we knew something about one of these numbers. If I knew this number was something kind of small, well, we need to get there with at least 8 more numbers. So 15 would be the smallest thing that could theoretically be. So if that was a 15 as a given, this would tell us that all the numbers from 8 through 14 are in here. Could we deduce what some of them are? This one right here, we said, has to be a prime. So yeah, we do actually know that these ones are primes because they're touching 2 and 3 and they're not 25. And 15 would tell us that this is some prime between, because we need to like sort of get up there through both of these ways. The minimum would be like 8, 9, 10, 11, 12, 13, 14, or some other arrangement of those. And so, is that right? 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So, what primes are between there? This has to be 11 or 13. So we'll write 11/13. Okay. And now, do we know things about other spots? This right here just can't be even and is in that range. So this could be 9, 11, or 13. And we got to super shrink that one. And that takes up 2 of the odd numbers in the range. So most of these are even. 4 of these are even, but they can't be, a lot of them can't be factors with each other. So like if that one's even, we're gonna have to be careful with it. So, or I guess not many in this range will be factors of each other if they're all between 8 and 14. So that 15 would give us a bit of info. As a test, we can always Command Z and go back. Let's see if instead of the 15, we'd been given something about this cell instead of that one directly above it. So this cell would require 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, a minimum of being 19. And if it was 19, I think this should work, because now all the numbers between 8 and 18 would have to be somewhere in here, which is a good clue. And 24 was a problem before, because it couldn't fit in here with the 6 and the 4, but 24 does work there. So the 19 there would actually tell us the 24 is right there. And let's see the notes. Wade said the rule about multiples of 5 made the last puzzle seem impossible. Let me double check real quick the solution I had with the multiples of 5 on that one. I'm going to double check my notes real quick just to see if I needed to edit anything on that one. Let's see. The one on the 4x4 grid, that one where the multiples of 5 are... Yeah, let's see. That one might be an issue. Yeah. That one has a different... This is, I phrased that wrong. You're right. This one was wrong. This one's supposed to be multiples of 5 are neighbors in some way, including diagonally with each other. So, that's a corrected version of this puzzle. That's what I meant. Neighbors in some way, including diagonally with each other. The multiples of 5. So, let me show the edited version of that real quick. Sorry about that if you already tried the puzzle. This one, multiples of 5 are neighbors in some way, including diagonally with each other. So, we also know in this one, going back to this one, the 19 gave us the 24. And let's think about some other extreme cases. Numbers that can't be, numbers that must be here in the 25's column must include the numbers 20. So that would actually mean it would have to be like 20, 21, 22, 23. But that doesn't work because 20 is touching 4. So, there, the 19 actually is impossible still because of that. So, if I had 20 here, we would know that of the numbers 21, 22, 23, 24, oh, we still know that's 25. We would know that of these numbers, up to 1 could be in here, and the rest have to be somewhere in here. So the thing is, 21 could only be one of these spots. 20's already been used. Oh, wait, something went wrong that last one. Go back. This might not have been an error. Oh, no, it was an error when it was 19. Now that it's 20, it would be different. So, 21, if it's there, can't be many places. 24 can't be... 21 could be these places. So we're going to shrink our text a lot to make 21 could be there. We're going to make a really tiny one because we're going to write a few numbers. 21 could be one of those spots. 24 could only be there. Well, I'm actually going to copy that to get tiny text. 22 could be any of them. And 23 could be any of them. So we wouldn't know quite enough with that yet. So the problem with these is they're verging between too much info and not enough info. Although, wait, we do know that these numbers ascend. So even though we don't need all of them filled, at least these 3 squares have to be pretty large because they're either these numbers or larger than these numbers. So this one is a minimum. These cells are at least 21. I'm just writing greater than 20. So if these cells would be greater than 20, because they're either these numbers or in this column with those, then the options for those are 21 doesn't work for any of those. So 22, 23, and 24 would have to be the 3, I think. So I think this would have to be 24. Wait, get my normal size back. And these would be 22 and 23. I think that's correct. So, if that's the case, down here we have 2 others, and a lot of smaller numbers are here. Almost all the smaller numbers on the way are there, but 1 isn't. So the other higher number was 21. And wait a minute, let me see. So we have 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20. One of the other numbers should be in this range. And then yeah, so wait, none of the bigger ones are over there. This has... Oh no, wait, we do have room for one bigger one in here if we wanted. But these still have to be that. These have a little more flexibility on what they could be. Now, leading up to the 20, are we going to have any problems with any numbers? Like 18 can't be there because of the 6. 18 also can't be there. We need some numbers around there. We could lead up with 17 and 19. What are going to be our most problem numbers? Well, what about the number 12? That can't be down in either of these. Can't be any of these spots because that's touching 6s or 3s or 2s or stuff. The number 12 would have to be one of these 6. So I'm going to make a little 12, or I guess a big 12 note in those for a second to note one of those is 12, but it can't be too close to 20 because we only get to skip one number in our path. This number actually, I guess we know, has to be either 18 or 19 in this case. And this one as well, right? Because we only get to... Oh, no, wait. These could be 17 through 19, I believe. Because they have to be pretty close to 20. Because we can't skip too many numbers. We could have a 17 there, and... Well, I guess, no, it's not that these two have to be, because one of them might be able to be a bit smaller. But at least one of them contains those numbers. These paths basically contain a lot of large numbers. So 12's not going to work there, I don't think. Although maybe, if we had the larger ones tucked in this direction. Maybe 12 could work a lot of places. And let's see how this could fit together. So the next number that's probably... No, 8 is definitely included there because these touch 4. So 8 would be definitely included here somewhere, and it can't be that bottom one because that's touching 2. So let's imagine 8's there. What would that do for us? That would just mean this is... Well, that doesn't work because this has to ascend. If 8 exists here, it's there, and it can't be down there. So it has to be there, because if 8's there, there's nothing else to put between them. But 8 can't be there because of the 2. I think we did hit another impossibility with the 20. Now, this is interesting because although I'm not finding a successful puzzle yet, whereas when I was designing them on my own, I would use certain rules to make it a little easier on myself. Here, having so many arrows sculpts it in a really particular way where a lot of numbers cause things to be impossible. So, or a lot of sets of arrows. We might have to delete that upper arrow and just give some more numbers as some information. Because some lowish numbers are going to block out certain factors. And they do have to ascend upward from here. So we know some things like 8, since all the columns ascend, 8's going to have to be on top of one of these spots, I guess. Because otherwise, it would have something in between it and something. So 8 could be there. Can't be there because of the 4. And these spots, I guess, would be including the primes right there. So if that's let's remove the p's. And no, I guess the 8 has to be there, or there for the next move. So it doesn't have a gap with a number we can't use. So 8 can't be here because of the 2 and there because of the 4. 8 would have to be here just from the 7. So I guess just having the 7 does give us more info we can roll with. I hope that just the 7 doesn't hit an impossibility. Oh, no, it did. If the 8 can only be there. Oh, no, this row, if this row doesn't have to ascend, we're good. So next would be 9 would have to be on top of one of these. So 9 has to either be there or there. 10 can't touch the 2. So it would either end up there or there, but those touch a 5. Uh-oh, 10 is going to cause an issue, unless I put it on top of the 9 there. That's the only way to dodge an issue. Okay, 11's a lot easier because it's a prime. So 11's going to be in one of these spots, and that makes it a lot easier as far as, I mean, harder on us. Easier for where it could land. Harder on us because it makes more options. Now, as for the 12 is either right on one of these or on top of the 11 on top of one of these. Can't be here or on top there because of the 4. Can't be here or here because of the 2. So the 12 could, and it can't be there because of the 6. The 12's either there or there. One of those spots has got to be the 12. Or up there, I guess. 12 is either there, or there. In this case, if it was here, it would be like 11 is there. That would imply the 11's there. The 11 would just be somewhere else. So let's see if we can take this further or if we need to add some clues. So here, if these strictly ascended, the numbers are getting bigger that we're filling in, so we're going to get less issues. So I think we might want to fill in one more number as a clue and try and do one that won't cause a bunch of issues. What if we put it in one of these 4 squares, something known, and let's say we know that from the beginning, one of our knowns being that, let's see, if this was, what number could this be at a minimum? Because it has to cross there, and there to make sure. Wait, no, it doesn't have to be bigger than this because we don't have an arrow there. So it can be anything that's larger than 11, 12, 13. 13 would be the minimum there. Now, let's say we knew that was 13 from the beginning. Let's say our givens from the beginning were that 7 and that 13. Then so far, we definitely could have already deduced this. Now what we would know is that it has to go 11, 12 based on our further deductions. Now, what about our 14? Well, our 14 doesn't want to touch 2 or 7. So our 14 sort of has to be there, or there, giving us a few options. What about 15? 15 can't touch the 3 or the 5. So the 15 can't be on top of there, on top of the 14, or on its own down there. And so I'm realizing one of the strategies of how to do this, or one of the ways to visualize it. If we can go in order by numbers up to some point, the next one's going to sort of fall in one of these spots based on that clue. The factor clue changes things. So 15 can't be in those spots. Therefore, 15 is in one of these spots. We would know. So one of these is 15. And what else can we deduce? What about 16? 16, I guess, could be a few places. Well, if 15's one of those, then 16 could only be on top of 14 at the most. So 1 in height on top of ness. And so it can't be there because of the 4. So 16 has to either be in one of these spots, and it can't be the lower one because of the 2. It would either have to be there, or it could be one of these spots. But with the 16 there, does that help us at all? There's no more multiples of that are worrying. So what about stuff that is going to have more multiples, like the number 20? Where could that appear? The number 20 can't appear in these cells because of the 5 and the 4 down there. And it can't appear in these cells because of that 5. So the 20 is somewhere in this upper region, and not there because of the 10. The 20 is one of these cells. So we might be almost at the point where we start having to mark things like that. But first, let's think about this column right here, because this leads up to the 25. And so the next number we're not sure about, I guess, is 14. Let's think of some extreme cases here. If this was 24, it can't be. So the most that could be is 23. The most that could be is 22. The most that could be is 21. That can't be 20, so the most that could be is 19. So that doesn't tell us that much yet, but it's less than 20 right there. Could help us, maybe. And it can't be any number less than 20. It can't be the multiples of 4 or 5. So let's think if we can narrow that down at all. That one, it could be 14. I'll make a little list to see if it's worth noting in it. Could be 14, can't be 15, can't be 16, could be 17, and it could be 18 or 19. So this one is, we'll just note it's between 14 and 19, because that might be useful. That means that this one is at least 14. I mean, it's at least greater than 14. This one's same but 15. And this one's same but 16. And we might even be able to limit those more, because the first number greater than 14 here is 15. And it can't be that. So it's greater than 15 there. We can sort of tick these up. And this one, greater than 16 could work. Greater than 17. That can't be 18, because that would touch the 6. So that has to be greater than 18. So that one's at least 19 there. And that might be all we can sort of do with the ranges right there. These 15s look kind of clunky, so I'm going to get rid of them. But we'll try and remember the 15s hanging out somewhere in that realm. And maybe working with this 6 and maybe with the 10 somehow, we can try and eliminate some of these possibilities. But we are going to probably need another clue that the viewer has access to. So what clue should we add that would steer this in a good direction? Well, if we knew something about one of these squares around here, that could help a lot. And for example, what if we knew, let's see. Well, these are arrows. So if up here we have, here we can't even have certain numbers because the minimum here, let's look at minimums in these extreme cases. That's a pretty extreme case. We found minimums over there. So here, the next number we haven't filled in based on, these were our two givens, the rest we found based on the arrows and rule. Let's say our next number is 14, which that can't be because of the 2. So that's at least 15, which it can't be. Can't be 16, so that's at least 17. So that's greater than 16. Now, that would make this greater than 17, but that's 18, which is 6, so it's actually greater than 18. Its minimum would be 19. So this has to be then bigger than that, greater than 19, because of this arrow. The first one, there's 20, which doesn't cause a contradiction. And this has to be greater than 20, but that would be 21, which touches 7, so it has to be greater than 21. So this one's either 22, 23, or 24, and 24 is a problem with 8. So that one's either 22 or 23. Now, what does that tell us? These can't be that. So this one's like, well, no, it could be one of those, but that takes up one of these here. And these are a lot of numbers bigger than this in this range. So this makes, and even here, let's just note the final ones so we have some things to work with. That has to be bigger than 13. That has to be bigger than 10, and that has to be bigger than 11. Now, here, how many numbers do we have that are similar things? Oh, I cut it off a bit. Let me get it framed better. How many things do we have that are similar large sizes? Well, the largest numbers... Well, let's also see... What about 24? That can't go that many places. 24 can only go in one of these three, just like 15. Is there another number with that trait? Or just those? What about the number 18? Can't go in those. Could go down there, maybe, or over on some of these. So, these are a lot of large ones. Like, how many numbers are larger than 18? Well, you have 19, 20, 21, 22, 23, and 24. 6 numbers. And this accounts for 4 of them with these right here. And maybe that can tell us stuff. Of the numbers in that range, 19, 20, 21, 22, I'll make this more visible, 22, 23, and 24, we need 4 of those in these really big ones. So 24 can't go in any of them. It doesn't fit in those spots. So out of these ones, we need 4 to go. So that sort of tells us a lot, because here we need 4 of those in these spots. That's almost enough to know exactly what they are. Close enough that we'll write their options, I think. Or no, that would have 5 options, because none of these really... Oh no, the factor rule would eliminate 21 here. I guess I'll write their options. 19, 20, 22, and 23 there. And here we could have 19, 20, not 21 in a similar way, 22 or 23. here. Oh no, here is another big one. 19 can be possible. 20 can't be because of the 5. 21 can't be. 22 can't be because of the 11. This one's either 19 or 23. So, this is getting almost Sudoku-like, but we also do have these column things. Let's note here, this has to be larger than that. So if that's 19 or 23, that can't be 19 actually. That one is 20, 22, or 23. And that's 22 or 23. And this almost tells us all of it, but of these bits, but not quite. So let's see, this is something bigger than 16, but it has to be smaller than one of those. Now this actually can't be 23, can it? Because that would mean 24, 25. And 25's there. That's only 19. That has to be 19. So I hope we don't hit a contradiction, because we're getting a lot of data just from this stuff, and I hope it all works out. If it doesn't, we will have found an impossibility in math, though, of this arrangement of arrows with that rule. Well, I guess, and these two givens, which then it tells us maybe even one given would have been enough if 2 is doing too much. But let's see if we can make this work. Here, our next number to find is 14. Well, how about this one right here? That has to be between 3 and 19, or between 17 and 19. So 17 or 18 right there, and it can't be 18. That has to be 17 right there. Now, what do we have left? Not that much. So 17, 19, and one of these. Could this be 23? No, because that was 22 or 23 and has to be bigger than it. That's 20 or 22. Now, I'm sure we can go further here. So let's see. 19 we can remove because it was used there. If this one was between 14 and 18, it can't be 15, so it's, and it can't be 16. So it's 14, 17, or 18 right there. Oh, not just re-italicize it and unitalicize it. Shrink it. Now, this one's larger than that and larger than that. What options do we have for some of these? Larger than 16. 17. Oh, wait, 17's taken. We can remove that from there. So that one's 14 or 18 right there. And bigger than 16, 17's taken. So you could have 18, but it's touching 6. So you could have 19's taken. Can't have 20, it's touching 5. Can't have 21, it's touching 7. This would have to be 22 and 20, because that's 23 by them not being able to be 24. So these would have to be that, and that would make that 22 and that 20. I hope this works. Let's see. I want to make these normal sized, though. No. And would this work? Let's see. Well, this could still be 14 or 18. If that's bigger than 15, there's 16. Can't be 17. So it can't be 16 because of the 4. Can't be 17. Can't be 18 because of that. This one can't be 19 because of that. 20 is taken. This one would have to be 21. And now how about these? What numbers do we have left? We have 14, 15, just making sure it all worked so far with our rules and our arrows. Our arrows are good so far, and I'm pretty sure The factor rule is good too. Yeah, our factor rule so far is good. So our numbers left are 14, 15, and 16 we haven't used, 17 we have, 18 we haven't used. And those are the only numbers remaining. So let's note our possibilities for each. 14 or 18. This one could be 14, 15, 16, or 18. This one, and that made it too wide. So this one, could it be 14, 15, 16, or 18? I think it could be all of those. And this would have to be bigger than it, so it could be those without the 14. And is there anything else that's a problem? Well, none of these have factor issues because the smaller numbers are mostly hidden. If that was 14, we would have some 15, 16, 18. If that was 18, we'd have some 14, 15, 16. And that does seem to work. I think we can make one final tiny clue and it'll all work. So what final tiny clue should we make? Well, these rows don't ascend or descend. I'm seeing if any arrows would work. No new arrows would work unless I do a double one that shows it's neither, but that's not even necessary. So we need something other than an arrow as a clue, such as another number. And to make this puzzle a little digestible, I think we can just list one of these numbers and know that even though other people may use that number to solve it a different way than I did, and it may make it quicker to solve, that it should work. So if this one was, let's give one that's the least amount of clue though. Maybe that, well, let's see, we need a clue that does tell us what all of them are though. So that doesn't quite work here with the last few. None of them by picking one would tell me about all the others. Or would it, with this having to be bigger than thing? Well, if that one was 14, that would have to be 18, and this would have to be a stack of 15, 16. So one here could tell us about it. Same with if it was 18, that would be 14, and these would be a stack of 15, 16. So we could either give the clue that like this is 18, or that this is 14, or that this is 18. Now, let's see, 14 is somewhat close to halfway to 25. So I'm thinking maybe 14 there would be good. But does that tell us too much about this too early? I don't think so. I think that'll work. If that's 14. Oh no, then these could be arranged differently. We have to give the clue about this one. So I'm going to give the clue it's 18 there, because that's not a huge clue, and it makes that need to be 14. So here is what we have. This, wait, 15, 16, and they have to be stacked because of the arrow. Let's double check that all of this is correct first. Does each one go upward only? Yep, 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 yep. Oop, I forgot to fill that one in. That one's a 14. Yep. And yep. Now, is anything touching one of its factors? So far, so good. I don't think any are touching any factors. Now, I'm pretty sure that this would be enough info for others to solve it. So, if we were to make this puzzle, what it would look like as a puzzle would be more like this. we would only be given, oops, well, these arrows and these numbers to start. And the instructions, which I might as well write in. So the instructions for this is that this equals column ascends numbers in column ascend size from bottom to top. Uh-oh. And let me get this where you can read it better. This is a bad place to write. They're doing weird spacing and stuff on it. So we'll put it down here and make it a little bigger. That equals that. And the sideways arrow equals that. And that we also know this. So that is the entire puzzle here. And I think that's pretty cool. See if any of you have any friends who are interested in puzzles, if they want to try it, print it out or draw it or something. And something like this, you'll also want to make the note, each cell contains a different whole number from 1 through 25. So this is basically what you could print or draw for them and see, or if you forget this later, the answer, you know, which you will before long, it's just a bunch of numbers and we'll see more of them, then you could print it out and try it yourself again, see if you could solve it, although you'll have some shortcuts on the way I approached it. Like I said earlier, it's very interesting with these puzzles how many ways you could approach it because you're looking at numbers. So there's so many different ways we could analyze numbers. Now, hopefully this isn't too easy or too hard, but at least I believe it's a solvable puzzle. It is easy to mix up sometimes when there's secretly 2 solutions or hopefully not secretly 0 solutions. But for now, this, I believe, is our first puzzle we have invented on livestream. Now, they said I have 2 22s. That's not good. So, we have to fix that. What went wrong? What number is missing? Instead, there's another number we must not have used. What is it? What's the number we didn't use? 18. 18 we didn't put anywhere. No, 18's there. What number are we missing? That's 24. Yeah. So, luckily, this works. 24 can just go up there, and it's not touching any factors. So, 24 shouldn't be an issue there to replace that 22. Because none of these are direct. Oh, no, it's touching 8. That's a problem. Uh-oh. This puzzle was unsolvable that way. So, wait, we're going to go back a few steps. Oh, no, it doesn't let me go back that many steps. So, the 18 was the last one we added when the rest of it was deducible up to here with an error of 22. So, that couldn't be 22, but all the other really high stuff's taken. So this is sort of going to cause a problem. Where are we going to fit this stuff? Because then some of these don't work. So, what is even just the 7 and the 13 too much? Because I don't know what I did wrong there. I hope that these were still deducible. But let's clear these and see, is there another way to lay these out? If I had 22 there instead of 23. And the biggest that could be would be 19, which I already used over there. So this is causing some trouble. So maybe let's just try one more thing. If 24 was there, 22 and 23 would have to be one of these spots. 23 is easy to place, so we'll save it. And 20 is there. We can't move it to one of those or there. What if we try and move 20 up there? But then 21 doesn't work there, and 23 is not enough. We sort of need the 20, and we sort of need that to be 23 in that case. And I don't think this is going to work properly. Let's see. 21 can't touch the 7. It would have to be there. 19, 18, we don't have anymore. 18, 21 doesn't work there, though. 21 would have to be there somehow. And then we would need 20 is there. 19 is, at least for now, there. What about 18? It can't touch 6. It could be there or there. One of these could be 18. If that was 18, though, there's not enough numbers that work to fit in there. So if that was 18, then we already used 17. Remaining would be 15, which is a problem. So what if 15, 18? Yeah, I could try and juggle these, but I don't think it works with the 13 and the 7. Okay, never mind about the puzzle being a complete solution. Now I am going to continue with trying a different similar style of puzzle, because it seemed really close to working there. And we saw that if we have a clue like a 7, that we can build up. Okay, so we're deleting this one for now. Sometimes you must try again. And with the logic puzzles, I notice I do make a lot of errors that I catch when double checking them, that sometimes I need to refine a rule. Or in cases like this, when we're designing the puzzle, we just hit a dead end. So if 7 told us that, what if we were a little and we know the 25's there just from these, if we have these arrows like this. What if instead we had known that was an 8? We would know it had to snake up like that. Or would it? No, 3, 4, 5, 6, 7, 8. It could snake up a few different ways in this case. So if that was an 8, what would be the other ways of snaking up? And would they cause any trouble? 1, 2, 3, 4, 5, 6, 7, 8. So there could be a few ways to get there. Oh, no, wait, that doesn't work because we have to build up to it this way and that way. So we would have to... This is actually the only way 8 could go, due to these arrows sort of steering those numbers right there. So what if we did have given at the start that that was an 8? How much info can we deduce from this? Well, here, these are primes, because touching 2 and 3 and not being 25. The number 9, which we want to place, is somewhat limited by the 3, but not super limited. And these do have to ascend. We are going to need some sort of other clue, and I think let's try something crazier. I think let's try if we have that arrow up there. And the arrow is going to tell us a lot about this line, but this is a lot more than an 8. But whatever number I put there, and we do know that has to be 1 based on these and that. Whatever number we put there, and someone said, I only have one ascending arrow on the bottom, so 25 doesn't have to be there, maybe. Well, in this case, I believe you're right until I place this. Now that I've placed this, the 25 will have to be there. But I believe you were right. When I just had 1 down there, we weren't guaranteed the 25 there. Although it is in a building from 2 ways place. But now this does change that. So the 25 is known at this point. But thank you for the correction on the way I phrased it, Tletna. And here, this number, what's the minimum it could be? Well, we have to get there 2 ways. We have to have all these smaller than it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The minimum that could be is 14. And if we knew it was 14, that could maybe be a fun opening clue. Because what that would tell us is that in some form, all of these spots are between 2 and 13. So now we're going to use our factor rule to see if we can eliminate what some of them must be. Well, one of these is 2. And then we sort of have to go over to include 3. These have to be pretty high up because they have to be significantly higher than these. So actually we're going to need a lot more numbers. 14 is not the minimum there, I forgot. It would include all of these squares too. So we're going to need to have something much bigger than 14 if that's our starting clue. We would need to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it would have to be at least 20 there. And all of these would be our numbers leading up to there in some way. These would have to be the numbers 21 through 24. So, how could this work? Would it work? Well, we can think of this 2 ways, the extreme over here or the extreme here. Let's start with the extreme near the 1. Where could 2 be? 2 has to be in either there or there. And following from there, 3 could sort of be on top of any of the ones here. So here, let's note, those could be 2, one of those. And one of those is 3. And one of these should be 4. So that tells us some info when we look at that in comparison to the 2. Like, if this is a 4, the 2, or no, that one's not problematic. But if this is a 4, that can't be where the 2 is, for example. That one would imply that. That one would imply that. And what about, if we go further, we just know at least 5, at least 6, at least 7. But that has to be more than at least 7 to get there. Because we also have this top arrow. So a bit more. What about this number? It has to be at least 1, 2, 3, 4, 5, 6. And not just 7, but 6, 7, 8, 9, 10, 11, 12. 12 is the most that number could be. And so let's say it's smaller than 13. Just because this is the symbol I have here. I forget how to make a greater than or equal if there's an easy way. And from there, what can we figure out? In fact, no, wait, it has to be even more, because all of the stuff has to sort of collect it up to get to there because of this top arrow. This top arrow changes a lot. We need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 at least to get there. So I think 15 is the maximum that could be. So I think it's smaller than 16 actually. So there is sort of a lot of possibilities here. Although we get to some trouble when we pack in our 2s, 3s, 4s, and 6s and such, remembering that they cannot touch their factors. However, I don't know if 20 is enough of a clue on its own for us to fully make it work. And oh, this is on a tilted desk. That was risky. So, oh, my classroom is somewhat empty because I just got a tent that I will be camping in the combo classroom with. So, it's going to be camping stream next stream, and maybe bonus videos, and part of the finale for my combo class channel, my other main channel, for anyone who doesn't know. While I'm saying stuff like that, last announcement I should say is I refixed the link to the combo class Discord, and I'm going to start checking there more and chatting with the combo community. So feel free to look at the link in the description for an updated link to the Discord. So, where we do have many combo lords chatting about cool things. So 20 on its own may not be enough of a clue, although we can note some interesting things. Like, each one, I believe, since we have to get there... Oh no, yeah, I guess the only path of numbers over there to a given number is to get up to it, and then to get over, and then also to go over and then go up. But no, since this one has to be bigger than those, to get to any, it is going to have to be at least the size of the grid it's on. So I guess this would have to be at most 10, at most 5. That would have to be at most 10, we can see, because we have to sort of climb up through two different things. So let's see what other ones we can find that are sort of extreme here. Like this one has to be at least 12. Here, I'm just going to write it like that. So kind of like 12 or more to mean. This one was 15 or more. And this one was 10 or more. So, filling in a couple of these, maybe this can help us when we find some more extreme examples. This one, for example, has to be 4x4, 16 or more to get to there. And similarly, this is another 12, and we get kind of symmetrical, although the 20 being in a certain spot throws off the symmetry a bit. So here, these parts are symmetrical in terms of the minimum amount of... No, this one doesn't do it. Hold up. These ones don't fully require all that, because these spots don't have the sideways arrow. It's kind of confusing to think about what's going on when we have the sideways arrow and the other one. What I think we might want to do is, because I'm worried this will cause another glitch, remove the sideways arrow, which, as Taletna pointed out, removes our knowledge of the 25 definitely being there, and just add a few more numbers that we do know for sure. For example, well, does that have to be 25? I think it might have to be, because if that was less than 25, where's 25 gonna go? 25, oh no, yeah, 25 could just go there without that top arrow. So, what if we did know that this was smaller, that this one right here? Now we kind of only have one definite path to carve there. And let's carve a path to a few spots. What if we knew that this one was 2, 3, 4, 5, 6, 7, 8, 9? I don't know if this is going to be possible, but if we were given that this was 9, it would have to be like this, which so far works for our factor rule. And I guess that could work, theoretically, because that didn't mess up any factors. If we were given that this was something, so that we can sort of close a gap that have different factor dilemmas and thoughts, this one is just going to have to be at least 5 due to that. What if we knew it was... Oh, but we already used 5, so no, it has to be at least 10, 11, 12, 13. If we knew that was 13... Oh, squirrel alert! Did you see it? So if we knew 13 was there, it would have to go like this, but that doesn't work because of the 2 there. So let's say we knew 14 was there. So let's see if this set of assumptions does better than our last set of assumptions. And either way, we have created an interesting mathematical problem. With this rule, on a certain grid size, we're just happening to use 5 by 5. And with these arrows in different places you could choose, and a few numbers given, which of those create an impossibility, which of those create a vagueness, and which of those might result in just a singular solution if we can find any like that. So here, 14 would tell us that between 10, 11, 12, 13, 3 of those are here. This can't be 10, so it would have to be 11, 12, 13. So, if we knew this, could we know any more knowledge about where things were placed based on our factor rule? Like the number 12 doesn't have that many places it can be. The number 12 can't be touching these 6s. Oh no, it's already there. Never mind. What about the number 24? Can't be that many places. It can't be touching this 12, so it can't be this. These are places the 24 can't be. That's a lot of places. So the 24 has to be one of those places. It also can't be there because that would leave 24, 25, with the upward direction. So one of these 3 squares would have to be 24. So let's note that. Now let's note 24, wherever it is, also helps us with factors because a lot of stuff now can't touch that. So how about another fact? Oh no, all the factors of 24 are down here. So what about other numbers that may be multiples of several things? Well, 16 is going to not be many places as well. 16 can't be anywhere on these edge bits. And theoretically, I guess 16 could be anywhere in that clump. And perhaps from here, we would need to add a third clue because there's enough different ways this could go now. The thing is, now that we've known that 9 path, this arrow became somewhat unnecessary. I wonder if there's a way, we'll try on this down here, if there's a way where, and here, the rule will be on top now. And in case anyone comes new, we'll copy this bit in the instructions for the arrows. So I wonder if it's possible to have our inner knowledge, our first knowledge, result in stuff about this inner zone and somewhat have paths open to what could go there. For example, if this was a little bigger than 9, we wouldn't know exactly what was leading up to it, which would be a little more interesting. Let's say this is 11. We're going to stick the 11 in a corner. And let's say we knew something about some other zone on the way there. And this can even be bigger than 11 in this case. So let's say we knew that one was 11 and that one was 13. What would we be able to build from here? Or no, let's put the 13 somewhere else. Let's put it there. Here we would know that 1's there, and it would be something like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 somewhere. What if this was 12? Does that work? Well, 1, 2, 3, 4, 5, 6, 7, 8... 9 can't go there, actually, if 3 was there. So 1, 2, 3. What if we went up this way? 4. No, we have to get there, though. So 1, 2, 3, 4, 5, 6, 7, 8. Well, these are all less than 11 in that strip. And these ones have to be on the way, but less than 12. So if that was 12, what could we prove? The 2 would have to be on the way to both. One of these would be the 3. Wait, no, but 12 didn't quite work. Because if the 3 is there and 4 is there, like, where's the 9 going to end up? This might work. If the 3 had been here, I think we would have had a problem maybe if we ended up using our 9 and stuff there. Maybe 3 could be there. So let's see if this path works. 4, 5, 6, 7, 8. 9 can't go there. So that doesn't work to go directly there that way. Does it work if my 3 went over there instead? So then over here, no, that doesn't work because where does my 4 go? So I don't even think a 12 works there. What other things would different givens give us? It's interesting to try and ponder. And sometimes we could even design it such that we know it's a type of number, but not a specific one. Like, what if we knew this was a square number, but we didn't know which one? Let's now see if we can try some puzzles along those lines, where let's say that we know that, well, what happens if I do fill in some square numbers on the diagonal? If 4 was there, I need to just get there from 3. And 2 needs to be somewhere else. But that's a problem, because 2 doesn't work anywhere else with the arrows. I don't think 4 can be there with our setup. So, what if I had a 5 there? Well, no. What if I had... Okay, what about the next square number? Does a 9 work there? What would this tell us? Well, 1, 2, 3, 4 to get to 9. That wouldn't tell us very much. 4, because then 5 could go a variety of places. Or could it, if we went like that, 5 would end up over here somewhere. But I guess that would work. So, I'm thinking we need one more arrow. But whenever I add the arrow, things get pretty crazy. We're going to try an arrow that's not on the top row. One in the middle row here. What will this tell us? Well, it tells us that if I want to get to a number here now, I sort of have to build to it in 2 ways. Because 1, which we know is there with the arrows, needs to have all of these smaller than that, and all of these smaller than that. So, if I, for example, knew this was 7, we would need to have 2, 3, 4, 5, 6... Oh, no, and this one, too, would have to be. So if this was 8, I feel like maybe we've been down similar paths to this before, but let's see what happens with 8 and the arrow there. We would know that we need 2 through 7 in this whole zone. 2 would have to be one of these starting squares. So 4 can't be there, but it already can't be there because of the 8. The 4 also can't be the other one of these that the 2 isn't, because the 2 is in one of them touching the other. So the 4 has to either be here or here in this case, with the 2 being the opposite one to it. And then 3 would need to be here. And then what about 5? 5 can't touch a 2. So if it was there, 5 could be some of these places. So 5 has a little bit of wiggle room. And 6, that might be an issue. 6 is going to be an issue. So 8 is too small to start with there, because where do I put my 6 now? It's going to bump into this 3 for sure. So we're going to need to start with at least a 9 there. And we're going to see a similar thing where I guess it's might still be similar to this, but now these could theoretically go 1, 3, and 2 is one number that we skip on the way there. If we do have a 2, does that cause a dilemma? Well, 4 can't be there, there, there. 4 can be a few places now, though. 3 can't be there. So maybe a 9 there works as a clue. Oh, I wasn't even thinking about what this arrow can tell us as much. So, like, that's bigger than that, for example. So, with all of these things being bigger than different things, we know that is bigger than all the ones that aren't. Those two are the only ones that could be bigger than that, because that one, due to the arrows. So the maximum would be if those are like 8 and 7, and that one was, or would the maximum, could it be 8 and those? The minimum it would be 8, 7, and 6. So this should be at least 6, but it has to be between 6 and 8 because of the 9 there. This one's kind of similar. This one, all of these, or it's not quite the same because our arrows. Let's see. This one has to be bigger than that and that. It doesn't have to be bigger than that, I guess. So it just has to be bigger than at least a couple. What can we learn from this? Well, the 9 doesn't give us any full info. Maybe we do need a starting one that will somehow give us full info of a chunk of here. So to get there, the minimum would be 12. Is that possible to get to a 12 there, if that was our starting info? Well, let's see. To get to a 12, we would need to use all of them. So it'd either be 2, and then the 4 can't be touching that. So the 4 has to be sort of separated from that to some degree. Going from this way, well, I guess it's not on the line anymore. Let's say the line did go to the number. Now, here we have a lot of stuff that it has to be bigger than because of those arrows. So we would need 11 to be like one of these cells. And we would need 10 to be one of these cells. And so, what info can we get from this? 9 would have to probably be one of these cells. But no, these could, yeah. It could also be 9 and then 10, 11, 12. So actually there might be a few options here. Can we deduce anything for sure based on our factors? Well, 2 on this end is going to have to be one of these 2 spots, and the 4, which has to come kind of close. So 2 is one of those spots. The 3 could be one of these spots, or it could be here, one of those. Now the 4 can't be there because of the 2s, or can't be the other 2s. The 4 would have to be one of these spots, and whichever of these, if it was one of those, would determine a particular 2 it had to work with. And, wait, no, the 4 can't be there. That's too far, because we have to build up to the 12 using it. And factor-wise, next we need a 6. Not quite next, but soon. And 6 can't touch the 3s or 2s. So 6 is going to have an issue here. It can't be here because of touching the 2s. And, oops, no, what's happening? I changed how long it was, and you can't Command Z that, I guess. So, how can we make 6 not have a problem with all these? Oh, and also 12 can't touch the 4 right there. So 4 would have to be one of these two. And if 4 is that one, either of these could be 2 for now. If 4 is that one's definitely 2. So 6 now, if 6 were, for example, well, I guess we could have a 5 stacked and then a 6, and there's a few ways it could go about. But it can't be touching the 12 either. So 6 can't be in those. And it can't be in those. The spots theoretically 6 would be these ones. But each of these would eliminate a lot. Would they even work? If 6 was here, that doesn't work, because that can't be 2 or 3. So these ones can't be 6, because they're touching either a 2 or a 3. Or are they? No, that could be a 4. 2, 3, 4. So I guess 6 could be those, theoretically. I mean, what was the one here? Now, if I was a 6 here, these can't be 2s or 3s. The 2s and 3s would then have to just be here. 2, 3. This would have to be either a 4 or a 5, but it can't be a 4 because of the 2, so it would have to be a 5. It would go like 1, 2, 3, 5, 6. And then we would have to fill in the others. I guess that could maybe work. Let's remember that this has to be pretty close to 12. Hi, Sassafras. There's my new stray friend. Well, he's not stray anymore now. He has a home. My home. Sassafras. Well, he got officially adopted at the vet and stuff, too. But he's a very good boy. Hey, Sassafras. He's become someone who just loves his family and his house and getting pets on his stomach and sometimes getting treats, and he's a very good boy. Here, stay here, Sass, I'll pet you. So, there will be a bit about my now 3 cats in the finale on my Combo Class channel when that's done. So, with this 12, I feel close to us being able to crack what's where, but I'm not positive. These, remember here, aren't saying the only things these could be, but for example, 4 has to be in one of the ones we marked as 4, 6 has to be in one of the ones we marked as 6, and etc. 5 could go a lot of places, but what about 8? 8, could it even be here in terms of size? If 8 was there, then we could have like 9, 10, 11, 12. Yeah, that could work. So 8, though, can't touch the 4s or 2s. So 8 can't be there, or there, like anything touching the 2s. It can't be in the middle of those 4s there, because one of those is a 4. And let's see if there's any others. Whoa, he's climbing the fence. He just climbed up. So, let's see. 8 couldn't be there, or there. So we have a few options for our 8. And those, I think, were the only, or could these be 8s? I guess these could be 8s. Now, maybe we should just fill them all in to see if we get any Sudoku-like clues. But some, like 5, could be a lot of places. So, like, the 2's there, the 3's there, 4's there. So the 5's could be, like, here, any of these, well, not any of these, I guess, or maybe. So we may need another clue. This 12 is close, but what if we gave a clue to be able to put it together without too much guess and check or anything like that? And our clue should give us some info about which of the paths to 12 has some of the either lower numbers or higher numbers. And to do that, we could do something like make this an 8, maybe. Because if that's an 8, for 1, we would know that we have to go 9, 10, 11, 12, and that these are 9s, 10s, or 11s. We would also, or could we even make it a 9? Let's see if that works. That would make this a 10 and an 11 just by default, based on a very simple deduction. So, to get there, though, would we be able to figure this out? These can't be 2 because of the 10, but they also can't be 3 because of the 9. So we'd have to have 2, 3. This can't be 4 because of the 2, so it'd have to go 4. But now we have a problem because we can't put the 5 there because of the 10. So I don't even know if it works with a 9. Let's say it was an 8 instead. So now, if it was an 8 there, the 2 can't be in these spots because of the 8, so the 2 has to be there. The 3 now maybe has 2 options for a moment. However, if the 3 is there, that can't be a 9, so that would go 10, 11. And where would the 4 land? The 4 can't be here because of the 2. Can't be here because of size and the 8. So the 4 would have to go here because of that 2. Or, yeah, so we would actually need the 3 there. Now, what about the 5? Well, let's think about the 10. The 10 can't touch these, so the 10 is either this, this, or this. And if 10's there, 9's there. If 10's there, 11's there. If 10's there, 9, 11 is there. So 10 is going to, these 3 are going to have to range the 9, 10, 11 are these ones. So if those are 9s, 10s, and 11s on the way to our 12, and there's 3 spots for 3 numbers, kind of Sudoku-like, we would know that those are where those 3 land in some order, and these aren't those numbers. And so now we would be left with a 5, a 6, and a 7. But uh-oh, that doesn't work because 6 can't go anywhere. So we have actually hit another impossibility. And remember, we're treating the impossibilities not as a problematic error, but as an interesting thing about math, that we found a little impossible puzzle with 0 solutions, and now we can refine it until we look for ones with 1 solution. Now, it's interesting because when I was designing puzzles on my own, I was whipping out a lot of puzzles pretty quick. I made like 10 or so of them so far. But this one is a little trickier because I'm trying to give less info, like less random sentences, like square numbers are on top of their root or something like that. And more so trying to just give a couple clues because of these arrows. And the arrows end up dictating a lot, and so does the factor rule in a sort of weird way that makes it a little trickier to figure out which combinations will result in a puzzle or not. And here, let's see if that can't be an 8. And I don't think 9 necessarily worked either. 9 didn't work, I don't think. What if that is a 7? Can that tell us any info? Well, now the 2 could be either of these spots. Well, actually, what if that's 6? Maybe that'll tell us a lot, because 2 and 3 can't touch it. So if that was 6 with a 12 there, 1, 2, 3, 4, 5, 6 would have to be the beginning. Let's see, 8 couldn't go in any of these spots, so 8 would have to be one of these 2. 9 also can't go in any of these spots, so one of these would have to be 8 and one would have to be 9. So these are 8/9 in these. And 5, 6, 7, 7's missing. That's easier to place. 10 might be trickier to place. So this one's going to have to be 11 due to size. And due to the size of the column, it would have to be 10, 9, but that doesn't work with the 10 or the 9. They both hit factors. So that's another impossibility. I wonder if even having the 12 there is an impossibility. Let's just try and lay out. Here's what we're going to try sometimes now. When we want to know if something simple is impossible, let's see if we can just lay out the things in a way to get there, maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that one didn't work because of the 10. So, let's see. That didn't work. 7, 8, 9 wouldn't quite work either. 5. What if 5 was here? Or, how's this going to work? 1, 2, 3. Okay, let's try. Could it work like this? 1, 2, 3, 4. Oops. Well, then we would have to place 6 somewhere. 6 can't be those places. Now can't be those. 6 would have to be there. So 5 would have to be there. And then 7 would have to be one of these. And 8 would have to be nearby too. The only way to make 8 not an issue would be to do that. 7, then 8. But now 9 is an issue. I think having the 12 there is impossible. And now I'm wondering if this arrangement of arrows has something difficult about it. Let's just construct something that follows the arrangement of arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, this doesn't follow the factor rule, though. I wasn't paying attention to that. Let's try and make it follow that. 1, 2, 3, 4, 5, 6, 7, or we'll bury the 2 to make it easier. 7, 8, 9, 10. Oh, no, wait. I need to build from there. That doesn't work. 9, 10, 11, 12, 13, 14, 15, 16 can't touch 8. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So this is an arrangement that does follow the arrows, and unless I missed one, does follow the factor rule as well. And so there are arrangements that work with these arrows. In fact, I was planning this to even work with all the arrows. So, like, if we had a puzzle where we knew it strictly ascended, there are still a ton of ways to make it work and even follow our factor rule. So now what I'm wondering is, like, which of these... Wait, let me see. Yeah, so which of these could you give as a clue that might let you solve the rest? Let's delete this one up here. And let's see what happens if I take one of this random-ishly generated thing and leave one as a clue. In fact, let's make the last line a little weirder here, like a little more random seeming. We'll put the 22 there, the 20 there, and the 23 there. Now it's even a little more random looking. So... now let's take one of those numbers. And we already know with this arrangement, and we are going to put the arrows on all of them. We're going to see what happens when all of them have to do that. Because, like I noted, these still have tons of solutions. Until we introduce the numbers, seemingly. All the numbers I introduced were a little too close to the extreme or something. Here we can tell 12 is a bit closer to the corner where we start with the 1 than it was before when I tried one. And so that makes it easier because it's not as restrictive of exactly what numbers have to lead up to it as if a low number is kind of high up. So a lowish number that is kind of far up somewhere are going to be the trickiest. Now, what would happen if I knew this 8? Let's see what that will cause. If I knew this 8 and I already can deduce the 1 just from the arrows, then, oops. What? What's happening? No, the arrow go forward. What? Okay. Close enough. Oh no. Command Z, not Z. Okay, so 8 there. What would this mean? Well, 2 can't be there because that's touching the 8. The 2 would have to be there. And then 3 could go a few places, but 4 can't be touching the 8. So the 4 can't be on top of the 3 there, or on its own, or there, or on top of the 3 there. It has to be on its own there. And the 3 has to be somewhere else here. Not there, though. One of these 2 has to be the 3 because of the size issues. And let's see. But how does the 8 even work there? Because, yeah, I guess we have to wind on a different path. But this, I came to a different conclusion here because I have the 4 there, and the 4 ended up there in the randomishly generated one. So here, let's see if the 4 works there. The 3 would have to be one of these 2. And then 5 and 6, do those cause an issue? Because we have to get to the 8, and we don't have that many numbers to spare. So 1, 2, 3, 4, 5, 6. If 6 is part of this chain getting there, it couldn't be there touching either of the 3s. And it can't be those touching the 2. So 6 isn't one of these things on the way to the 8. 3 in this case would be one of the ones on the way to the 8. So it would be between 3, 5, 6, 3, 5, and 7. So these ones would be some combo of 3, 5, and 7 for these squares. If this is going on me putting the 4 there and not 3, 4 like that, which if this doesn't work, we'll try that because we'll have shown someone could have excluded the other. Where are we going to put our 9? Because that has to go somewhere pretty close here. It can go there, or there, or there. But it can't be touching a 3. And let's see. So this 8 on its own, I don't think is enough to give us all the info. Because there's multiple ways we could continue from there. But what if we had known the 8, and let's give one more number from our randomly-ish generated one to see what we can put together. We're going to say, actually I kind of like the 6 being there, seeing what clue that gives us. Let's see what happens if I know a 6 here, a 12 here, and maybe we'll give a 3rd, but let's see what we get from that to start. We know 1 is there, and I'm going to bold always the ones that are given at the beginning of the puzzle and not bold the ones that can be deduced from that. So to get to 6 right here, this has to be either a 4 or a 5, because 2 or 3 wouldn't work. And then 2 would have to be there, because 2 has to be sort of crunched in. It's small enough with these arrows. 3 now would have to either be there, which doesn't work from the 6, or there. So it'd have to be there. Now 4 actually can't be there because the 2 is there. So this would have to be 5, and we would have to put our 4 there. And then to get to this 12, we now have 7, 8, 9, 10, 11. That's 5 numbers that these are going to be 3 of them. If 10 can't be any of them, and so what about 9? 9 could be there. Let's look at the possibilities of each. 7 could be any. 8 could be just this one, potentially. 9 could be just that one, potentially. 10 can't be any. 11 could be any. And that's all. And this is great because Sudoku style, we can now show that, and similar for many grid puzzles are sort of like this, we have 2 options between 2 cells, so it must be exactly those for these 2, meaning they're not for that one. That's not 7 or 11. That's an 8 or 9, and those are some ordering of 7 and 11. And the thing is, if this was 11, that doesn't work for that to be an 8 or a 9. So it actually has to be a 7 there. We'll make it big size again. And that makes that an 11. And this has to be an 8 or a 9 on the way there. Our 10 now would have to be tucked in somewhere kind of close. And so far, let's just see if the deductions I've made ended up the same as the grid. So far the deductions I've made are us figuring out that portion of the grid given that we had 6 and 12. This is like a whole family of math problems you could ask about a single puzzle, about some formation of it, which combos of numbers give you the right solution. And here, let's see if we could prove anything else right away, or if we would need more numbers. I think we'd need more numbers to go onward from here. We would need some other clues. Now, the next one I was thinking of incorporating was this 20 up here, because I'm trying to use ones that, to a degree, have a good amount of factors, so they'll help us with clues. Although the factors of this are hiding all the way down there. Squirrel time again. He already has a nut. Do you see him eating his nut? Wait, the squirrel's being cool, so I'm going to show just the squirrel for a second. Can you see the squirrel eating its nut? I hope I got the right angle of it. It's hard to tell with this glare. Yeah, he's back there. You can hear it eating the nut. There it is. Friendly, cool squirrel. Let's get a zoom in on that squirrel. There's that squirrel eating his nut happily. Okay, that's enough for our squirrel intermission. Let's go back to our puzzles while the squirrel hangs out with us. And what we were looking at is what other givens we might be able to add to this puzzle based on an arrangement that we somewhat randomly generated that we know works, that with certain bold numbers given we can deduce others. And my next one I wanted to add was the 20 there, and seeing if we had that as knowledge as well, what that would be able to help us deduce, and if these clues would make a puzzle from that. So and I'm learning new strategies in this stream for how to design these arrow type puzzles, which I hadn't really tried before. Now, or this factor rule. So here, this is somewhere from 13 to 19. And actually, maybe, let's actually, let's maybe actually try and find a number with more factors around. Oh, there's another squirrel. It's a squirrel meetup. Or is it trying to steal the nut? I think they both got some. Oh, that's so cool. They're both there. One sec. Uh-oh. Can you see them? Wait, I have the wrong angle. Double squirrel. You see the double squirrel? Now that's combo. Now they're playing or something. Okay, that was a good little squirrel interlude. And given that we've been going 3 hours, I need to take another very brief break. Again, I'm going to go back to the puzzle I made before out of several puzzles I've made. I just need to run to the bathroom real quick. And now I've fixed it. So, this is a different puzzle. It's not this. I filled in the grid down here for something else. This was the one I showed you. This is the ones that's a little different. Just imagine a 4x4 grid. This one I don't have the grid for, but 4x4 grid with these rules. So, while I'm gone, this is the fixed version of that if anyone wants to try. Earlier, I accidentally wrote one part of it wrong. But the crucial difference from before is that multiples of 5 are neighbors with each other, not with the number they're a multiple of 5 of. I'll be back shortly. I just have to run to the bathroom real quick. And I will see you all in a couple minutes. Okay, so I'm back, and hopefully some of you have fun messing around with that puzzle at some point. Now, looking at this, one thought I'm having about this is what it makes me realize is that the types of grids you can make where they strictly ascend in each row and each column the same direction would be the same if these went the opposite way, just flipped. But all of the ascension happens in one direction for rows and columns. There's a particular set of numbers that works like that, a really large way of arranging them, but like the set of ways to arrange it is large but specific. Because when I was picking random spots for them that I thought would work for a number, it often caused a contradiction with just like two numbers. But now, even when I put a third number, it's like we have to think about all these clues to try and get there. And it won't cause a contradiction, but I almost think we might need a fourth number to actually get there with this, despite earlier, like, two numbers causing a contradiction. So I'm curious about, for different sizes of grid, what are the rules about which types of number fulfill this? It seems like it would be a pretty simple thing, but when we mix our factor thing in, it's quite different. That really complicates it. But even just for which, like how many different ways could I make the numbers without the factor rule ascend in a singular direction for rows and columns? And which numbers would be inherently impossible? Because like even without my factor rule, as a really simple case, the middle square could not be 3 with these arrows because 1... 2, anything else will be larger than 3 on one of these arrows. As another really trivial example, the number, let's see, how would this be? The number 1 we know is in the corner, but another thing we can note is that, like, the number 2 is at most 1 in some direction there. The number 3 is at most, even under best case scenario, which doesn't even work. It's going to be more than this. So actually more like at least. The number 3, so at least. The number 3 is going to be at least, well, at most or at least, depending if we're talking how close or how far. So 3 cannot be many places. Because to get there from 1, most spots 3 has enough things that would have to be larger than it. I think this square right there, the minimum would have to be 6, because otherwise how would we get there in less than that? And I do believe the minimum for a square, without the factor rule or anything at play, is the size of the rectangle it forms. Like this is a 2x3 to get there, so the minimum there would be 6 in a certain puzzle, I believe. Here, I think the minimum would be 9 to get there just from the arrows, not related to my factor rule. So the minimum is somewhat easy. Maybe that would help see how many different ways you could do it. Although the factor rule greatly complicates things. Now, this factor rule is only one of many possible rules we could do. And not being able to touch their factors is one thing. Being able to touch their factors is another. And why don't I just try one or two other random examples after this? First, let's see if we could fill in this grid with these clues. Well, here that was either an 8 or a 9, but we're not sure which. Next, where's our 10 going to be? 10 has to either be there, or if that's 8, 9, it could be up there, I guess. Oh, no, wait, yeah, so we have 8 and 9 on the way. There's one extra, so 10 could be one of these. Actually, 10 can't be these because of the 20. So 10 could be there or there. There's a few places our 10 could theoretically land. What other numbers have a good amount of divisibility with these? Let's see. I think it's weird, but I think there's multiple puzzles that would work with these 3, even though we kept hitting glitches with 2 numbers. Now, I'm going to leave this as an open question for this part of the stream that we're going to change gears for a bit. An open question of what does it take on this sort of layout with all these arrows going in our ascending ways? What sorts of numbers as givens on here are impossible combos? For a single number, I think it's the size of the rectangle there would make it impossible. With the factor rule, perhaps more for certain spots. But what for different combos of numbers creates impossibilities? Or which ones create possibilities that are or aren't good clues, like open-ended ones or ones that give you other definite things? Now, let's experiment a little more with thoughts about factors and things, because sometimes I was making slightly simpler rules, because can't touch leaves a lot of possibilities compared to when we know things are touching some type of number. So let's try inventing a puzzle using the arrows here, but that also has some, and for now, we're going to keep it strictly ascending in different ways, like all the same direction for these arrows. Let's now make some sort of rule or two based on what a number has to touch. And earlier it was, I think, let's see who recommended this. It was Wade recommended this earlier, that we look at prime factors. And I have looked at numbers factors in general, but prime factors could be interesting as well. What if we do have one of our rules be numbers cannot touch or can't be neighbors with, including diagonally, any of their prime factors? Now, the first thing we can note, and this would be easier on a smaller grid for sure, so let's consider if we want to try this on a smaller grid to start. What if we start on, just to see what patterns emerge from this, I often started on a 3x3 grid to see what was possible there before expanding. Also, Wonder Bucket asks, what's the number of the day? And what is the number of the day? Let's go with, now I want to do a square number because of all these square grids, but we already, to a degree, I think the last stream had a number of the day that was a square number or something like that. So let's think about what makes sense for the number of the day. The number of the day will emerge in this puzzle. This puzzle will tell us what the number of the day is. So with these arrows, we know 1's there and we know 9's there. If numbers couldn't be neighbors with any of their prime factors, 3 can't be in any of those. So these are the possibilities for 3. Now, the thing would be 2 has to be buried by odds. And we only have 5 odds. So the only way to bury 2 with odds at this point, given that these are in the corners, would be for 2 to be in one of these corners. Can't be in that one, it can't be in them due to size, though. 2 is supposed to be one of these. This won't work on a 3x3 puzzle with prime factors and these arrows, because 2 is going to have to touch something else. We don't have sort of enough odd numbers to make it work. However, maybe it'll work on a larger puzzle, but I'm not sure if this one will work in general, this combo of rules. We sort of have the ascension rule and the prime factor rule. So here we'd know 1 and 16 due to the arrows. Now we know 16 can't be touching 2 anywhere around there, but we also know that 2 itself has to be buried by odds. We have 8 odds total, one of which is used. So 2 couldn't be in one of these spots, one of these 4. Or no, this one might work. But it couldn't be in one of these 3 because it would require too many odds to fully bury it. But also, wait a minute, the arrows tell us so much. The 2 with the arrows has to be in one of these spots. So one of these has to be a spot where we can bury the 2 with odds. And yeah, Wonder Bucket says the last number of the day was 25. Since we're doing squares, I think we'll say the number of the day is 16. I know it's similar to last time that it's a square number is the reasoning, but square numbers show up in these a lot. I was also using traits like which things add up to a square number for some of my other puzzles as clues, like some of the puzzles clues where this row has the same sum as this or something. Now, here, that would actually be an interesting way to try this puzzle as well. Instead of the prime factor rule, having the rule be that some row or column must add up to something, particularly maybe this diagonal or that diagonal would be interesting to know if they added up to something particular. What if we knew, for example... Okay, we're going to try prime factors in a second. I just have another number pop into or another thought about numbers pop into my head for a moment. This is going to be, what if we knew each diagonal adds up to a square number? Is this possible? Well, here, to make that work, 16 plus 1 being 17, the distance to the next square number, if it's 25, we would have to have these two cells and each diagonal individually. I'll note it's not like the combo of them, but each diagonal separately adds up to some square number or another. The distance to 25 is 8, and then the distance to 36 is 6. What's that? 19. And then at some point it'll be too big to add, but not yet. So the distance to 49 next would be 32. The distance from 17 to 64, that would be 47. And that is at the point already where they couldn't add to that. In fact, we went further than we need because they can't even add to 32 if we're on a 4x4 grid. So in this case, these two would have to either add to 8 or add to 19. Is that possible using our arrow rules? Well, first let's see, is it possible for them to add to 8? If they add to 8, this has to be bigger than this because of the arrows. And it has to be at least 2 larger than this because of the arrows, because of these things on the way to it either way. So to add to 8, it could be 3, 5, which I think we'd be able to quickly show is impossible, or 2, 6, which doesn't even work because 2 and 6... Oh, no, wait, if we're not doing the factor rule, then this doesn't work for a different reason, because these two would both have to be smaller than 2. So, what about 3, 5 doesn't even work, because these can't be smaller than 3. So, if this diagonal added to a square number, and let's even first just say the knowledge we have is that this diagonal does, then we'll see if it works that the other one does. So it would have to add up to 19 for these two. What knowledge could that give us? I mean, this has to be at least 2 less than 16, up to 14 there. So we'll say 14 minus, like it's 14 or less. Or I guess I'll put up to 14, like looking like that. And this one, well, now it looks like negative 14 is the number there. But you know what I mean. We'll put it after. 14 or less. And here we have 3, although, no, it can't be 3. It has to be at least 4. And it can't even be 4 because 2 would have to be one of these on the way. 2 and 3 would have to be these. And those have a factor with 4. No, wait, we're not doing the factor thing. I forgot. If we're not doing the factor thing and we just have to make it work this way, could it still even work? 4 and 14 would require us to crawl up to there in a particular way that probably could work. That would make Oh no, it has to be less than 14. It has to be 13 or less. So like if that was... Wait, no, but that would be 13 and 5. Yeah. Because 13, 14, 15, 16 would have to be what we get. So this is one case that could maybe work here if we don't have our factor rule yet for that. So I'll go back to the prime factors one, because that's a new puzzle, but we'll leave this as a question for later. Is it possible to make this? Somebody investigate this on your own if you want, and leave a comment on the stream video later of whether you can make one or both diagonals add up to a square number under these conditions. And also keep in mind, we're just on a 4x4 grid right now. There's various options. So now let's look at the numbers can't be neighbors with including diagonally any of their prime factors. Does that work? Well, 2 has to be one of these. And 4 can't be that far from these, but 4 can't be touching the 2s. So we have another case where like 4 could be there or there, there or there. And so wait, first let's just actually think this way. We have to bury the 2 with odds because the 2 can't touch any evens. So one of these places, the 2 is next to the 1. And it's going to need 4 other odd numbers surrounding it. The odd numbers have to fulfill this thing of it working. So, if this, one of these is it, and the other is an odd number, so 1 is 2 and 1's an odd number of those, and this is an odd number, and let's see. Odd, odd. We need to bury the 2's regardless. So these are like dependent on where it is. If it's there, it's odd, 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 odd. If it's there, it's odd, 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 odd. So these are like dependent on where that 2 would land right now. Now, in either case, we have to get up to an odd that's at a 6 rectangle here, which makes that odd need to be at least, and you know, we have one little problem here I just realized. Without any other numbers here, this is symmetrical in a way. We will have the duplicate solution down there because although that looks like up, that's also up. So you can either orient it where one's up and one's the side, or one's up and one's the side. And if we don't have any other info to make this less symmetrical, like if these arrows were on the other side here, you would see the symmetry a little better. Then there's definitely going to be a mirror solution. We'll never have just one solution exactly. There would be a flip of it. So what that means is that this type of puzzle would need an extra piece of info to have a singular solution. Because of that, we're going to note that, let's just say, to avoid flip solution, let's say, here's how we'll avoid the flip solution. We'll say we know the 2's there, because the 2's either there or there. And by saying the 2's there, we've broken the symmetry. So that works. Trust me that it's would be the same thing if it was there, if we didn't have the clue that it was on a particular side. So symmetry broken. Now to get here, this is a 6 rectangle, which normally would make its minimum size 6 on this type of arrow thing. However, they're all odd, so the minimum size is a little bigger, because we would have to go something like 3, 5, 7, 9. And so the minimum size of this one is 9. That one's at least 9, 9 or more. These ones are at least 5. And it's odd. So, I will... This looks like a blood type I'm writing out. But come on. Oh, it's because it's on the other line. Okay, too small. No. Okay. That but 9. And that same thing. And this one's that but 3. So it's 3 or more odd, 5 or more odd, 9 or more odd, etc. So if numbers can't be neighbors with, including diagonally, any of their prime factors, well, let's see. Actually, that one could be a 3, I guess. 3, 5, 7, 9 would work. So that could be a 3. And that one we did know is 9, but we don't know which way we approach it with the 7. So what about some numbers that are going to fall soon that conflict with this, like 6 or something? So here, we need an odd to land there, and it has to be a smaller odd than that. How big of an odd could these even be? Because here it's like 15 is the maximum of that square. 14, I guess, just based on having to get there. From the 16, that would have to be at least 13. I mean, at most 13. So this would have to be at most 12, because 12, 13, 14, 15, 16. And no, that wouldn't even work to be 12, because we would also have to get there other ways. Like these would be larger than it too, but have to be smaller than that. So here, this has to be a pretty low one. The 3 has to fall either there or there. If the 3 doesn't fall there, let's say it was the 5, then we need to get there from both with the 5. That should work, I guess. Let's see, what can we know from this direction? The 16 can't be touching 2, but it's not. That's okay. As far as prime factors, it can't be exactly 9 and 3 right there. That would conflict. What is too big for this? What's the maximum of it? If it has to be at least 9, well, it can't be bigger than 13, because if it was 14, 15, 16. So this one would have to be either 9 or 11. Or could it be 13, 14, 15, 16? No, because it also has to get there from there. This one is a square away from that, like the opposite of 1. I could now see this square as a 2 by 3, which is 6, and subtract that from the 6. And note that this has something to do with 10 as far as a limit, because here, if it was more than 10, we wouldn't be able to fit, say it was 11. 12, 13, 14, 15, 16, or I guess 11 works there. Interestingly, does it? 11, 12, 13, 14, 15, 16. I guess 11 does work there. 1, 2, 3, 6. Why is that? I guess that makes sense, because from 1, when we ended up at a rectangle, I wasn't counting 1. So it was actually the rectangle size minus 1 of the distance from it. So the rectangle size of 2 by 3 minus 1 is 5. 5 less, because we have to count it, even though the 1 snuck past that. Makes 11 possible here. So this is either a 9 or an 11, right there. Now, here, that makes this very limited. This could only be a 5, 7, or 9 because of that. And this one right here could only be a 3, 5, or 7 because of that. Because remember, we need odds to surround the 2. And this one maybe has a good amount of options, but it can't be too big. So, has more options, though. I guess I'll write them. I think this could theoretically be 3, 5, 7, or 9. And here, what would these different things mean for our factor rule? Well, if that was 9, that would have to be 3, because 3 can't be there, and 3 has to be somewhere around here. This almost means that these are all full of these specific odd numbers, apart from the chance that that one's an 11. Can we somehow disprove that being an 11? Let's see. 12, 13, 14, 15, 16 would maybe work. We would have to tuck some stuff somewhere. So where else can we go from this deduction? This might need another clue to be solvable, but I'm not even positive it has a set of solutions. So let's see if we can go a little further. Now, 9, 3, 3. Some of these spots are going to eliminate a lot of multiples of 3. What about the number 3 itself? 3 is either there or there. Or would it be possible to just have 5, 7? No, 3 has to be one of those. And 3, kind of like 2 had a shell of odd numbers, 3 needs a shell of throd numbers, numbers that are not threeven or not multiples of 3. So, for example, 3 needs to be surrounded by things like 4, 5, 7, 8, 10, 11, 13, 14, and not 15, and 16 is already used. So 3 is going to have a shell around it, and this case has 3 more things it needs in the shell, but 2 that aren't part of this thing. This case has 4, but also 2 that aren't having notes about them yet, that would need to be among this list. Some are impossible, like, well, wait a minute. We can actually prove stuff faster, maybe, if we just start looking at 4. With this 2 here, the 4 has to land pretty close. We either need 3 lands there and 4 is on top of it, or 3 lands there and 4 is right after it. So either this one or this one should have to be 4 for the rules of these, based on which of these is 3. And 5, we noted, lands one of these. If that was 5, we would have 7, 9. So wait, if that was 5, this would have to go 3, 4, 7, 9. What about 8? Where's 8 gonna fall with all these 4s and 2s around? And someone here left a comment. I wonder if this is a set that they solved for this. Now, and they asked what if you allow 0 to be placed, but also this is a set that maybe works for this. Let's see if it does work. And I'm assuming you mean from top to bottom it would have to be. And so let's try the one you suggested, from Asterios Chrysophudis. And leave a comment on if you got this from deducing it, which would sort of imply that if you're right, it's the only solution, or if you just sort of plugged in different possibilities to find a solution that worked. Like whether your deduction showed this being the only one or just a possible one. Because if it was just a possible one and you were correct, this would mean we would need more clues to give a viewer. They would need more givens. Although, if you were able to deduce it yourself, that would be enough givens. So, wait, no. Wait, I was looking at the wrong line. 2, 7, 8, 10, 1, 5, 6, 9. So let's see, does this fulfill the requirements of ascension? Yep, each of these is ascending. Does it fulfill our other rule where numbers cannot touch a prime factor? Looks good. The only prime factors we will really see here are 2, 3, 5, 7, 11, 13. So, and 11 and 13 won't be the prime factor of anything here. 7 can't touch 14. 5 can't touch 10 or 15. 3 can't touch anything 3 even, and 2 can't touch anything even, and that does look good. I am curious, Asterios, whether you found this by deducing from the clues and had any spots where you just filled in something that worked, or if it seemed to be the only answer. I will experiment with that more on my own in the future. What it would mean essentially is how many givens do we want to give, like the 2 was already there. Asterios noted that it's definitely not the only solution. Some can be swapped, such as the 14 and 15. So that's good to know that this is one example, as well as this being another, of a possible setup for this puzzle. Numbers can't be neighbors with, including diagonally, any of their prime factors, and we have the ascension rule. And based on different combos of these numbers, perhaps even just one, but probably requiring combinations of them, you could deduce that it is exactly one specific layout like this, or like the 14-15 one. So, perhaps I'll experiment later with which of these we would need to give somebody, and you can feel free to experiment and comment as well, all of you, which we would need to give somebody for them to be able to deduce an exact state of it for sure. I knew we needed at least something to break the symmetry, but we're going to need probably more than one number given. Now, this is just one of many possibilities, of course. This was numbers can't be neighbors with, including diagonally, any of their prime factors. But other things that I've been experimenting with include if we said how many odds or evens are in a given row. If only some of these ascended or descended, or if only some were given and they were flipped other ways, what would that be like? I haven't even been sure whether there are any combinations of arrows that are inherently impossible regardless of numbers. I'll think through that later. And other things would be, does it add up to a square number or prime number or something like that? Or maybe even if you just knew it added up to even or odd, that would tell you certain things about the parity of their evenness and oddness, although not everything. If you knew 4 numbers added up to something even, you'd know it's either all evens, 2 evens, or no evens, for example. And you could make notes about the diagonal sums and stuff like that as well. For example, some of my puzzles relied on the diagonals having the same sum as each other. And let's think about some other options for some puzzles. Let me actually just pull open my notes for a minute, because I might be wrapping up the experimentation part of this soon. We are getting close to 4 hours long on this live stream. But pulling open just some notes I've been taking about this, about other things that would be fun to experiment in a puzzle. And let me know if you invent any combo grid puzzles of your own. And let's see. Here's some that could be interesting, are making some equations. For example, noting the top left corner times the top right corner equals the center, or something like that. Or sometimes equations that, you know, it either adds or multiplies to the result, but you're not given which. And other variations, of course, could include negative numbers or fractions. You'd have to come up with some rule, such as a fairy series or stuff like that. Or, the fairy sequence, where you'd have to have some way of deciding which fractions were included, like up to a particular denominator size and numerators being smaller than that or something. With negatives, one I do want to explore more is a 5x5 grid where the numbers range from -12 to 12, including a single 0. I also had the thought that some puzzles could be fun to have sort of like blank spots where you have like a crossword, like someone mentioned, squares blacked out. However, instead of blacking them out, I think we should make them zeros. So I think that some puzzles you could be given, you're only using the numbers 1 through 12, even though it's a grid of 16. So one assumption of a combo grid puzzle is if you saw a 4x4 and, well, I guess not an assumption, it would be written in there, but some of them would note that you only use integers from 0 to some size, and that all the integers from 1 to that size occur exactly once, then you know all the other spots must be zeros. So some puzzles could be fun to have masses of zeros in certain ways, whether we looked at their sums related to things or whether you had to use them to maybe they don't count for a certain rule about things can't touch. So you might have to surround numbers like 2 or 3 with zeros if possible. And there's many ways we could use those zeros. Perhaps you get clues on lines and columns of how many zeros are in that row or something. Now, other ones one thought was, I want to kind of write a guide, maybe a book someday, of puzzles that can be played with some certain amount of dice on a chessboard, because those are common things to have around. Chessboards such as that one, and dice such as these ones. Everyone has a floor of dice, right? No, but everyone does often. A lot of people have dice or chessboards around. So a lot of these could, if your numbers ranged from 1 through 6, but you were allowed more repeats, you could design some interesting puzzles. I did also think repeated numbers could be okay in some. Perhaps you note that something like you have 24 numbers on a grid of 25, and one number repeats twice. Perhaps even more numbers are allowed to repeat, but each line tells you within this line, like each row or column, tells you how many duplicates there are. So thoughts like that are further types of puzzle that I want to try to design. And if any of you design any of your own, let me know in a comment. It can be kind of hard to describe them, but you can still do your best to describe the visual thing. Some of them, like these we've seen, can be written purely in words. If some of your words are on a 4x4 grid, then also just experimenting with different board sizes. Another one would be arithmetic progressions and geometric progressions, like 2, 4, 6, 8, or like 2, 4, 8, 16. That's arithmetic, then geometric, from 2 with a certain ratio of growth. Those could be interesting if you were told this line contains an arithmetic progression, or maybe you're just told it contains one of those 2 types of progression. Although geometric progressions quickly grow too big to fit on the board, but some would fit. And in general, rules about evens and odds, and more rules about threevens and the 2 types of throds. These are some things that I would like to work into more future puzzles. And I think to wrap up our puzzling, we will do one more casual while I read through some comments. Star Battle. Now, there is a daily Star Battle, which is one of the simplest grid puzzles, and in my opinion, even cooler than Sudoku due to its simplicity and awesomeness. Where you essentially have a grid that has some shapes outlined on it. Some different grid sections are within a shape or another. And with that grid, you need to place a certain amount, like a 3-star or 4-star puzzle, a certain amount of stars within each row, column, and shape. And why don't we do a star battle for fun to wrap it up? Later, I will go back to more of my own puzzles because I have a bunch of half-cooked ones that I'll finish cooking up and share with you folks in a later stream, or maybe I will write some texts about them sometime. But for now, I'm going to star battle for a little bit on a slightly bigger than usual, not the largest size, but slightly bigger than usual. Not just the 3-star, the 2-star is the most common, but the 4-star, which there's a website here that has a daily new one. And I figure, why don't we play today's 4-star puzzle? 4-star does not mean difficulty, and they don't rank the difficulty of these daily 4-star puzzles, but you know, they're usually not that much harder than the lower amounts of stars, but they can range. Some of these puzzles are much harder than others. So we'll see what today's star battle holds for us. Here it is. And again, the rules are that I can place exactly 4 stars, and I'm going to either mark squares that aren't a star with an X or ones that are a star like that. And each row, column, and shape contains exactly 4, in this case, stars. Now, the final note, if anyone leaves early, like I mentioned briefly earlier, I fixed the link to the Combo Class Discord, so click on that in the description if you want to chat with other Combo Lord people, or post on the subreddit, which I will check what's happened on there again soon, or just in the comments here. And make sure that you're all also tuned into my Combo Class channel, where the finale of Grade -2 will be coming before long. The camping I will be doing in the classroom the next few days is one of the last parts of the finale to film, although it will require a lot of editing. Now, I'm going to look at these shapes and see if I can place 2x2 squares over them that cover them all, thus, but leave one of the squares covering a small enough section that I know the star must be there. Like one square, and then it can't be the edges that would destroy that square. One square right there is different, and one square there. They fit within 2x2s in a way that tells me these must be the stars. I will make a longer guide later. Wait, it turned red because they're touching. So yeah, they're not allowed. That's the other rule I forgot. You're not allowed to have stars touching, meaning neighbors, including diagonally or orthogonally. I always forget to say that rule. It's right over here are the rules on top up there. But 2 or 4 stars in this case per row, column, or shape, and these being the shapes. And each star cannot be neighbors with another. So, I'm not going to fully explain what I'm doing with this. I've done somewhat of explanations in previous streams, but I'll mostly save those for when I make a full episode about star battles. They have a lot of cool math, but I'll just half explain as I go. Let's look at the small shapes. This could fit 1, 2, 3, 4. And this one could fit 1, 2, 3. We need these stars there, and that's most of the ones in that line. How about this shape? 1, 2, 3, and a bit more than helps. 1, 2, 3, 4. That's a good one. And that will cut off there and there. How about, is this too big or not? 1, 2, 3, 4. We get some knowledge from that. Now we have 1, 2, 3. That cuts off those edges, and that's all. Or these also go. That there. How about this one? 1, 2, 3, 4. And we have 1, 2, 3. And let's see. Where else is small to begin before we look at lines and other strategies? 1, 2, no. 1, 2, little too big. What about this one now? 1, 2, 3, 4, and a bit. So the smallest ones give the most info. Here's a pretty small one. 1, 2, 3, 4. That has to go. Those have to go. And that shrunk this a bit, but not fully. So now we're going to look at, well, let's see. Let's do this shape before we move on. 1, 2, 3, 4. 1, 2, 3. That's all, I guess. Yeah. So now we're going to look at some lines and other strategies, or any lines starting to fill up. That one can fit 1, 2, 3, 4, and a bit, so not quite. We're getting close to the point where lines will give us info. 1, 2, 3, 4. What other shapes are small enough for us to investigate? Well, how about this one? Does this have 1 in there? Because we only get 1 more star in this whole massive line. If this doesn't have a star there, it has both of those. If it does, those are wiped out. Here we have 1, 2, 3, 4, 5, 6, 7, 8. It's also helpful sometimes to look at how many 2 boxes can fit in a pair of rows or columns. Sometimes you'll see me counting out boxes like 1, 2, 3, 4, 5, 6, 7, 8, and a bit. And we're looking for times where it's 8. Or even an 8 that's partially cut off is even better. But we're not going to see only 7 fit. Otherwise, we messed up something about the puzzle, because 2 lines need 8 stars. But if we see more than 8, we can't really apply our technique. So I think we need to spend a little more time on shapes. 1, 2... It can't be there. That would destroy too much. What about there? That would also destroy too much. What about there? That would also destroy too much. What about there? That would also destroy too much. I'm not sure if that helped, but let's look at this line. 1, 2, 3, and a bunch. Not quite. So, any other shapes shrinking around here? Let's see. 1, 2, 3, and a bit. And I will be checking the chat while I do this. We're not speed doing it right now. So, thank you to all of the notes. Somebody said maybe I could call the game Optimus Prime. That would be good for one related to primes, and there are some that are even more related to primes, so maybe we'll save the name for one of those, like where primes can't touch each other or such. And I did notice that if your rule is primes can't touch each other, including diagonally, on a 3x3, they have to be the corners. So that's an interesting way to say the corners are clues on a or the corners are primes on a 3x3, is to say the primes aren't neighbors in any way. And then they have to be there for 2, 3, 5, 7 in our typical range. On up to 16, the amount of primes is 2... There would be 6 primes up to 16, so there'd be more ways to fit those. And then here's the interesting one, too. Up to 25, there are 9 primes. And so if we said on a 5x5 that primes cannot touch, including being neighbors or anything. In fact, on a 4x4, I don't even think we could have that rule, because I don't think it would fit right. But on a 5x5, it perfectly works. On a 5x5, you can have precisely 9 things not touching if they are the corners, the middle of each edge, and the center. So, good night to the folks heading out, like Asterios. Everyone's in different time zones, so I totally understand. Remember, if you folks are ever bored, how many live streams I have saved as videos. So if you're ever bored or need something to watch late at night or while you're half focusing, there's a lot of live stream content in the vaults. And the finale I'm working on will be a pretty long thing too, but unlike my unfocused live streams, it is going to be a more cinematic, somewhere between half an hour and an hour. So, any other knowledge we can scope out here? 1, 2, 3, 4. This one keeps looking smaller than it is because it has a star hiding there. 1, 2, 3, 4. I'm just revisiting some places that we have semi-proved. And how can we go further from here? I feel like there's got to be a way. Well, we can't have 2 in this. So we must have 3 between these. So it can't be these spots, because they would force 2 in here, which makes this line have too many. Could it be there? If I was there... 1, 2, 3, 4. That could maybe work. What about here? Can we eliminate that? This would not only remove these, but function as a line destroyer with the help of those 3. So it would remove these and these. And that would make this shape not fit 4. So it can't be there, and that's cool, because now this shape is known to a degree. We know that it's like 1 in that square, 1 in that square, 1 there, and 1 there. Now, can we do my box technique yet? 1, 2, 3, 4, 5, 6, 7, 8. So that one does just fit, but it didn't give me any new info, but it did just fit. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So those aren't giving me any info yet, unfortunately. Now, let's try some other things. This line's getting pretty close, but not quite filled in. What about this region? Can we do any interior eliminations where we destroy too much of the inside, even though it counts as a star? Maybe not in that one. What about some interior eliminations on any other ones? Okay, here. How about an exterior elimination? Not quite. Here, what are our possibilities? 2, 2, 2. Now, another strategy that sometimes helps is looking at a certain amount of rows or columns from the edge and seeing to what degree a certain amount of shapes fit in that or poke out. Like, if I look at what's going on in the first 4 columns this way, we have 1 full shape, 2 full shapes, 3 full shapes, and 1 bonus star there. So that means all we have left in these 4 is 3 more stars. And those 4 included all this. That, due to the rest of it not being huge, needs at least 1 star in there. This over here needs at least 1 star. So I'm not sure exactly if we got any info from that, but there's at least 1 in there. And at least 1 in that whole chunk we knew. And so that might not give us any info yet. But we can always look at other directions if stuff like that helps. Within a certain amount of rows, are there a certain amount of shapes that mostly or completely fit within those? So I'm not sure if that technique will work at the moment. Let's see what other shapes or lines we can do any eliminations from. Let's see if we have room for the box technique this way. 1, 2, 3, 4, 5, 6, 7, 8. Yes, this might help. 1, 2, 3, 4, 5, 6, 7, 8. Yep, since those 8 fit, we know it's 1, 2 is there, and that eliminates these. How about here? 1, 2, 3, 4, 5, 6, 7, 8. Yep. And 1, 2, 3, 4, 5, 6, 7, 8. So that did work. Let's see what that told us. 1, 2. It only works if we're at exactly 8. If there's more than 8, then we can't use the technique. There's wiggle room for where they could be. 1, 2, 3, 4, 5. That didn't tell us anything new there, but it is showing that it could help somewhere here. 1, 2, 3. No. Okay. So maybe not right there. Where else could this maybe be helpful? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 8 and a bit over there. So that technique doesn't work until our board's a little more full, maybe. And where can I go next from here? There's got to be a next spot where we can mine out a new clue. Oh, I got it. This is 1. These 2 right here are stars, and so that's 3 in a line. And this must contain at least 1, because we can only fit up to 3 in that part of the shape. So that must contain exactly 1, because that's what fits 4. And so those are gone, but we also know that contains exactly 1, and these must be there for that shape to work. So that gave us a lot of info. Now, here there's only 2 more spots where it could be, but we don't know completely in that line. Here we have a few gaps as well. 1, 2, 3, 4. And now let's see how that helps us with shapes. 1, 2, 3, 4 means those are gone. Any other shapes getting small? 1, 2, 3, 4. Ooh, this shape's small. 1, 2, 3, 4. 1, 2, 3. And 4. So that helped a lot. Also made some other shapes smaller. This one now we know is there. All right, now, do we have any more 4 in a lines to look out for? Maybe not yet. Here, though, we have all X's until 1, 2, 3, 4 is all that fits, and we get to remove all the neighbors of those because they're 1 by 2s, and that's a technique you'll notice when you play these a lot. So 1, 2, 3. Although I don't play the 4-star ones a lot until now. Now I'm hooked on the bigger amounts of stars. I used to only do the 2-star ones. So here we have 1, 2, something, something. So that one not quite small enough. 1, 2, 2, 2. Some of these must have gotten small enough for us to pull some shenanigans with. Let's also look at some notes of here. Let's look at lines for a sec. 1, 2, 3, 4. And this makes this 1, 2, 3, 4. So that's helping us with these shapes a lot. Now, this one must be 1, 2, 3, 4, and those are in a line with the 3 stars. So those have to remove the rest. Got a bit of a ripple effect going here. And any further we can ripple this. 1, 2, 3. Maybe not. Let's go back to our box technique, see if things changed. 1, 2, 3, 4, 5, 6, 7, 8. That fits normal. 1, 2, 3, 4, 5, 6. Okay, this is good. 1, 2, 3, 4, 5, 6, 7, 8 means that and that. And did that shrink any of these shapes enough? This one still has that bit attached. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So these must both be it, I guess. Is it true? Yeah. 1, 2, 3, 4, 5, 6, 7, 8. So these are both it. So it's not there. But it has to be there because we had here 1, 2, 3, 4, 5, 6, 7, 8. And I'm looking at boxes. How many 2 by 2s can fit in a place? By box, I don't mean the shape. I mean a 2 by 2. So that takes care of this whole line. Now, this one is is left. And so if it's those two and those two, it's not that. Here we now have 1, 2, 3, 4. Where we basically know where they are in pairs of 2. Now let's see what we can do from the other direction, looking at rows. Can we do any of this square technique? 1, 2, 3, 4, 5, 6, 7, 8. Yep, so here, 1 box, 2, 3, 4, 5, 6, 7, 8. Now looking at this area, we can see 1, because we're looking at this type of box. 1, 2, 3, 4, 5. Oh, and actually, this is known, so that gets eliminated. 1, 2, 3, 4, 5, 6, 7, 8. And that tells us it was this one. How about here? 1, 2, 3, 4, 5, 6, 7, 8. Not only do we get that, but we proved several. Well, 2. And here, do we have any more 4s? We got a bunch of 2s and 3s going this way. So let's see. This shape shrunk. And this has a lot of X's. We can fit 1, 2, 3, 4 exactly, so all the neighbors get removed. How about here? 1, 2, 3, a little more than 4. Not all the neighbors get removed, but trust me, those ones do. Now, where else can we extend this? All right, we're going to use some more box technique. That was working really well. So 1, 2, 3, 4, 5, 6, 7, 8 shows it's that. Here, 1, 2, 3, 4, 5, 6, 7, 8 shows it's that. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This one's extra good. This one, it fits in a smaller amount of space, so we get to cut out every other neighbor pair. That leaves that, and that. Now, this shape has 3 and 1 in there. And 1, 2, 3, 4, 5. So it needs to have 3 of these, so none of the ones that eliminate 2 at once can be there. Now let's see down here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that fits normal. How about here? 1, 2, 3, 4, 5, 6. Even more, so it doesn't even work there. Okay, what next? This line got pretty ready. This one's close. And let's also keep an eye on when we have these 1x2s, if they're in the line with several stars, because they effectively act as a shooting thing that direction, like this and those two. I mean, there's only 1 in the rest of that line right there. So there's only 1 within those because of these. Only 1 within those at most because of those. Or actually exactly 1. Exactly 1. And so that means there should be exactly 2 in there. 1 there and 1 there. That makes sense, because 1, 2, 3, 4, 5, 6, 7, and a bit. But so if I do know there's 1 there and there, because of the shape, 1, 2, 3, 4, 5, 6, 7, that means there's only 1 in this 2x3. If there's only 1 there, that shape's still too big. Anything about this we can do? These shapes are shrinking, so let's recheck them. 1, 2, 3, still several options on some of these. So the box technique always does me good, so I'm going back to that. And we're going to look at 1, 2, 3, 4, 5, 6, 7, 8 doesn't quite work. 1, 2, 3, 4, 5, 6, 7, 8. That's the one that already was really helpful. 1, 2, 3, 4, 5, 6, 7, 8 does not tell us a ton. 1, 2, 3, 4, 5, 6, 7, 8. Same. Oh, this one told me something. Eliminate those. Now I'm going to come back to these now that they changed. Okay. Okay, that 5, 6, 7, 8. So it's not that. Now up here, 4, 5, 6, 7, 8. 5, 6, 7, 8. So we have that, and then 3 more in that shape. This line's also almost full. And 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Like I mentioned earlier, I will do a more thorough tutorial on all of the techniques I use, and even some techniques that I've almost never used but technically could work in a certain circumstance. There's a lot of really nifty techniques to this, and it's a interesting game theory and game design concept as well, so there will be a main episode about this someday. But if you don't fully understand, just imagine me laying a lot of 2x2 boxes over stuff and seeing how many fit, because that's a lot of what I'm doing with the techniques. And also sort of recognition of certain shapes that I'm used to on smaller amount of star puzzles, because in one of these, where some of the stars are already gotten, it sort of reduces to a 2-star or 1-star puzzle within that section, or line, or whatever. So 1, 2, 3, 4, a little too much there. Where will this help next? 3, 4, okay. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, not quite. 1, 2, 3, 4, 5, 6, 7, not quite. 4, 5, 6, 7, not quite. So I need to figure out one more breaking point, because I may have run out of what the box technique in that exact form was. Oh, to whoever asked what I'm doing, because they just got here. Earlier in the stream, if you comb back through that, I was inventing some puzzle concepts and testing them out. Right now I'm doing an already existent puzzle called a Star Battle, and if you want to freeze your frame on it for a moment, those are the instructions over there. You can pause there and read them if you didn't catch the part where I explained it. But 4 stars per row column shape, no stars can be neighbors. So the simplicity of the rules, yet the amount of different puzzles that work within its rule set, is part of why I like it so much. 5, 6, 7, 8. And I figured using shapes like this could be interesting in the type of puzzles I was designing as well. For example, if each shape contained exactly 1 square number. You would also have the same amount of shapes as one side of your square, which this has to have mathematically. You'd also need to have that there, so like a 5x5 would have 5 shapes if each one contained 1 square. Or you could have the shapes all have the same sum, or something like that. So, where do I break through the rest of this puzzle? I know there's got to be a way. What I might have to do is start doing my 2 technique and taking mental notes of where exactly shapes land in these things, where like my guaranteed spots are in different ways of looking at it. Like 1, 2, 3, 4, 5, 6. Oh, that actually helps. We have a new one here. 1, 2, 3, 4, 5, 6. No, not quite. 7, 8. That tells me, for example, there's 1 in one of those 2. And that might not necessarily help right away, but if I figure other spots they must be in a shape, it could help. Let's see if I can isolate within this bigger shape that, like, 1, 2, 3, 4, 5, 6, 7, 8. Those bottom 2 squares do each have 1. 1, 2, 3, 4, 5, 6, 7, 8. That square has 1. 1, 2, 3, 4, 5, 6, 7. That has 1 apart from that. So whether that exists sort of hinges on the fact if those other 3 have 1. Let's see. We're getting small. Oh, here, this line has gotten down to 1, 2, 3, 4, all that fits. So we can eliminate the neighbors of that line, and that helps a lot. Now that makes this one 1, 2, 3, 4, and the neighbors of that get eliminated. And maybe we're getting a whole little chain reaction that I just missed the clue of. There's several places to look for clues in this puzzle, so you have to look back and forth sometimes between shapes, lines, and a few other things. Let's see what we now know about some of these lines. 1, 2, 3, and a bit more than 4. We can eliminate certain neighbors that destroy too much. And did any of these get closer going this way? Not sure. Well, now we are going to retry running our techniques of 1, 2, 3, 4, 5, 6, 7, 8. Checking boxes. 3, 4, 5, 6, 7, 8. Checking how many boxes can fit in a particular zone. And 1, 2, 3, 4, 5, 6. Not quite. And trying to find cases where the amount fits. Oh, wait. Oh, yeah. Where the amount fits within 8 that we can identify for 2 lines. And see if that gives us new info. 4, 5, 6, 7, 8. 4. Now here it's not going to help that way. We would have to get one going this way, which is a little trickier. 1, 2, 3, 4, 5. Nope. Nope. Well, can we do any more this direction that help in any way? 4, 5, 6, 7, 8. Or 2, 4. This shape's getting kind of small. 1, 2, 3, 4, 5, 6. 1, 2, 3. If I was here, that would eliminate too much of that, because we'd only fit 1. That would be gone. 2, 3. So that spot eliminated too much, and now that shortened this line. So that makes these be there. Now, we're getting close to having lines of 4 pointing this way. All of these low ones have 1 star left that they need for many rows in a row up till there. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Now we know that's that. And does that help us any further? We have to see, where did the ripples happen? What got affected? I can't be in there. That would destroy too much. Just a random thing I noticed. And 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Not quite. The block technique doesn't work when we don't have enough crossed out stuff at the right points. 1, 2, 3, 4, 5, 6. Nope. So, did any shapes get more manageable? When that's gone, this shape needs 2 of these. So, can't be at those spots. Those eliminate too much. And is getting us close on some of these lines, but close isn't quite enough. What about here? We have 1, 2, 3, 4, 5 possible. But do we have both of them here? That would be 3 in this line. What about this line? 1, 2, 3, a little more than 4 still. So we have 1 there, 1 there, 1, 1. So let's see. This zone we noted only has 1 to make these lines work. Here, if we have 1, 2, 3, 4, 5, 6, that doesn't quite work there because we're not sure it's there. It's one of these 2. So if it's one of those 2 for the shape here, that means it's one of these 2. And this needs 1 missing, and that's in the way. And this leaves 1, 2, 3, 4, which is a lot of info because all these neighbors can go. Then in this shape, 1, 2, 3, 4 is necessary for this shape. And that actually fills this whole line. Now, 1, 2, 3, 4. So, oh yeah, that now has to be exactly that. And that neighbor can go. And here we have 1, 2, 3, 4. So 1 is there. That tells us that. And that. And these. And 1 of those. So, how to figure that out? Here we have just 1 left. And this whole zone, I think we'll be able to tidy up right now. Perhaps this ripple effect will even take us all the way to the end of the puzzle. 2, 1, 2, 3, 4. There we go. Apparently we solved it in 33 minutes, but we weren't speed solving. We'll do speed solves another day. Right now I can solve the 2-star ones unbelievably fast, but I don't have much practice on the other levels of stars. So thank you to everybody who is looking at some notes. David Hodge says I should take a peek at what he found about prime numbers. Yeah, sorry. I have been so slow at responding to people, but now I've rebooted up the Discord, and I'm going to check through my emails during this finale season. We are wrapping up grade -2. It's October. In fact, I got some decorative pumpkins, but they're out in the front yard. They'll be here next time. Next time that I stream, maybe not the next short or bonus video, because I already have a few filmed, but at least the next time I stream will be camping in the combo classroom. And as you can see, I have cleared out quite a space here that will fit a new tent I got. And we'll see what types of nighttime critters want to join me in this space I have cleared. And I will make a campfire out of bricks. I mean, the bricks will surround it for safety. The campfire will be made of logs and things. Anyway, thank you all for joining me. That's going to be all for today's stream because it's about to be 4.5 hours. I knew I would get carried away with this because the past few days I've just been having fun trying to fiddle around with what makes different puzzles work. And as a reminder for anyone who missed the beginning, this is the type of puzzle that we ended up sort of fiddling around with what was possible and what wasn't possible earlier in the stream. I will continue to create puzzles, and I will see to what degree the arrows can be a main aspect of a certain type of puzzle. I do believe, if you ever want, that you could design your own puzzles simply not with extra rules about factors and stuff that we had written here, but simply with having arrows and a few numbers filled in, and maybe one bonus rule or something. Maybe extra square on the squares that have square numbers or something bonus to make it more interesting to solve. In any case, I will keep you up to date with all of my strange puzzle fiddling around withs, and there will be a lot more bonus combo content coming soon, but do make sure you're also tuned into the main combo class channel where the most polished and best episodes go. Thank you all for joining me so much. Check out that description if you want links to things like the Discord link is working again, or other links and such. And appreciate you all for joining me here. Time to wrap up our 4.5 hour